The following message is best viewed on an oscilloscope.
Hello, everyone.
Hello.
Hello, I guess we start.
Hello, Martin.
Hello, Martin.
Hello. So today we start a second session of Education and Outreach track at ICHEP. Welcome, everyone. And I will be chairing together with Mira today. And in the first part, we will continue the discussion that we started yesterday about gaming in education, and we will learn about open data initiatives. And after the break, we will also learn about how different institutes are organizing educational programs. And we will try to also make a photo again today before the coffee break. So let's see how this work out today. So Pierre, so I let you start. So just a short intro about Pierre. So Pierre is a CMS physicist from CNRS in France, and he will tell us well, how in fact we can have CMS experiment in a pocket. Yes?
Yes, exactly. Thanks a lot, Martin.
Okay, so the floor is yours.
Okay, I hope. Does it work? You see my screen?
Yes.
Okay. So indeed, our project is to enable everyone to be able to share our very nice CMS experiment by just taking your smartphone out of your pocket. So this is something between serious game and demonstration tools. And just a small history. In 2018 already, our technical director started thinking on virtual reality potential for research and developments. And he made some private work on this, private visualization of the CMS detectors. And then the lab decided it was something useful to go on. And we attributed the project to our engineer, Jérôme Oslet, under the responsibility of Daniel Bloch, one physicist, chief of our group, and myself. And then he had Evan Display, use the possibility to use on many platforms, PC, headsets, smartphones, and so on. In 2019, I presented the status on the first status in the CMS outreach group, and there I received many attention and help, mainly from Tom McCauley for Event Display from iSpy, and Alberto Zambrotti for the full plan of CMS CERN. Now the team at IPHC is, as I told Daniel Bloch, a physicist, Laurent Gross, who is supervising as a technical director, Jérôme Oslet, who is doing the tough job, and myself also to supervise and trying to find the best way to progress and to present things. We do not come from the vacuum. We have some nice inspirations from Bell 2 virtual reality presented at ICHEP 2018. There you have a wonderful event visualization with precise information on each track. So this is very good for a pedagogical point of view. Of course, I already told about iSpy. It's also very interesting because you have a direct access to a web page. You don't need any special tool. So it's easy for people to share. That was one of the things we found promising. And it's easy to use the information for the event in CMS. You can take the information from this program and to use it. CMS itself was represented in 3D dimension in SketchUp. So you have a simplified 3D representation, which is also very nice and very useful for us. And of course, you have a huge picture library for CMS, and this is really required if we like to make something very realistic. So these are our inspirations, and our aims is to show the detectors in details and to explain how particles leave signals in these detectors, and also from the detectors signals, how we can reconstruct the particle tracks. So if you see a picture of a small detector, a tracker end cap, and on the right, you see the image produced with iSpy, where you see all the tracks and also the hits in the detectors. This is typically the kind of thing we'd like to reproduce in another environment. Our aim also is to have people feel and interact with the gigantism of the experiment. So that's why we wanted to make use of the virtual reality, and we wanted everything to be as precise as possible. So we rely on exact technical drawings and pictures. We want to propose pedagogical information. As I showed you, the event display explain how it works, how we can reconstruct the tracks, but we can go beyond that and explain how from the event dynamic you go to the publication. This is something we think about. It's also possible to insert posters, explanation, whatever. This is kind of thing we are thinking about. But very important for us is to enable anyone to share this with friends. Therefore, we target mainly smartphone, but you can combine smartphone with cheap headsets and have virtual reality feelings. And the system will also be available on other platforms such as real headset, computers, and so on. And of course, in order that the application is shared, it's best to make it fun also. So technical point of view, about the software, we use 3D Studio Max for the object mapping and the track animations. And we use Unreal Engine for the interaction with the target device, smartphone, computers, headset, interactivity for the user, scenario, real-time rendering. Okay, then let's go. First step, implement the detector. So from CMS SketchUp, we had to redefine all volumes. So this is just an inspiration. We really had to redefine all volumes. On the left, you have the CMS SketchUp image, and the two right pictures are from the VR screens. So we also mapped textures either from pictures, or we produced the texture from matter effect inside Unreal Engine. And we also inserted a human in order to feel the scale. It's called the third-person mode. Step 2. Let's go to iSpy and implement the event. So on the left, you have iSpy results. You can export the event from this, all the event information, and using a small homemade script by Jérôme, you can import it in 3ds Max and animate the trajectory. It's produced the small film I'll show. If it does not work properly, you can have a look at the Vimeo link shown on the slides. but you see how it looks like. And it's really near what you have on the left picture. So this now we can do nearly automatically for each event available in iSpy. So you can run on different events. And step 3, the cavern. For Alberto Zambotti files, we took them. They were easy to import and to give drawings looking like the one on the left. However, you have also to apply texture in some place and to also apply interaction between the scaffoldings, for example, and the character. Does the character go through the scaffolding, or is it blocked by the scaffolding? All these have to be defined. So we did it, and you can see what it makes. So just a small example how you can go. Again, the video is here. You can look at the Vimeo if it does not work properly. We decide to be able to walk in the air in order to go close to the interaction point and really see the collision at a human scale, and to see the detector's details. You can remove also the detectors by just typing a K or putting it again. Then you can walk around. And just to show you some examples, I will not make the whole trip, but you can have a look. You can put some posters, maybe you recognize them. And let's look at CMS itself. Imagine using headsets. You see this in 3 dimensions. This is really impressive. And then you can start playing and going around in the cavern. So again, I will not go everywhere, but just to show you, you can both go to the stairs here, or in the tunnel, you will have access to the lift of CMS to go on the ground level, or to the main staircase also to reach any level you like. This is possible. So you have the whole plan of all the tunnels, all the rooms of CMS. Here, for example, in this image here, I put the character at the top of the CMS well at 0.5. You can go and look downwards, or you can go on any scaffolding, or in the lift here, or in machine rooms and so on. This still needs developments, but there is a huge there is a huge potential, I think. So future extension is to improve the scientific information, implement a game scenario. This is quite important. And also be prepared for CMS upgrade. It's coming soon. We are preparing some real CMS upgrade in Strasbourg. We would like to implement it also in the virtual reality at pedagogical posters also. Of course, the COVID-19 produced some delays and some changes. For example, the headset version, we decided to postpone it because of sanitary condition. It's probably problematic to use. And instead, we reinforced the smartphone and computer version. And anyway, the software availability is delayed. About status and availability, the preliminary headset version was already used with visitors, students, and so on. It's still under development. Desktop version is foreseen for exhibition room inside our laboratory. And the sharing of the first beta version will delay it. Probably it will be available by the end of the year. And for more information, of course, you can contact me. But we like to go forward. And we are seeking new collaboration with computer scientist schools. I already contacted some of them, and probably we will have some students next year. Game developer, people from science education. And then we foresee several tests with masterclass students, PhD students. And also more on the research path, we intend to use the acquired expertise to develop interaction with objects designed in CAD in order to test the object before we realize them, before they really exist, and to manipulate them and so on. And also the other possibility is to use it as a practical tutorial for detector assembly. So that's it. Thank you for your attention.
Thank you very much. So now we can take some questions. Do we have time, Mira?
Yes, go ahead.
Yes. Do you have any questions? We will see. If we have many, then we will use the raise hand option. No one? Okay, I have a question.
Yeah.
If I can ask. So you mentioned that, first of all, it's really impressive. I'm looking forward to see this project live. But you mentioned you will be reaching out to computer scientist schools. How you envisage to collaborate with them? Would you be inviting them in like development part?
Yes, I think, well, the first step will be to propose some work for students and to co-teach the students with a project. Then we'll have to see how it's going on. There are people specialists in the rendering, people specialists in the virtual reality, but the teacher there are not yet really interested in our project for their research. It's not a research project for them. However, they will be interested to have students working on this and helping with the project. It will be a first step.
Yeah, I find it quite nice as a solution for you to in fact advance with the project and then to allow students to participate in the development as well. Yes, I see there is a question from Peitsa.
Yeah, hi. I was interested about what sort of gaming scenario are you proposing for the project? Will there be a global leaderboard for the students, or will they just be wandering around the virtual station, or do they have some sort of progressive quest through the facilities? Or
yeah, that's the difficult part, and we have to find the best solution. It must be possible to implement. It's not yet completed. We are at the start of this research. Probably we would like something with a progression indeed. Yesterday I heard some other ideas like hiding Pokemons inside caverns and things like that. That might also be something different. If we go on the pedagogical side, it would be nicer to, for example, try to build CMS step by step and try to understand how it works. And once all the detectors is built, you can make the the collisions. That would be one possibility. But I think there is a good potential with the large area of tunnels, because people like to move around and discover some hidden place. Even for us, they are hidden places when you go through the game. So, but we are open to proposition, of course.
Thank you, Pierre.
Marzena, if you got, I didn't see how to raise my hand. I don't know if maybe I'm still a co-host and I'm not allowed to do it. Sorry.
Perhaps, because I don't see this option neither. I think when you are a co-host, you cannot see this option.
Okay. Okay. Anyway, I don't want to talk out of turn, but I just wanted to make a comment. So I guess I will talk out of turn. Anyway, I think this is really nice. I really appreciate what you've done here. And I do like this idea of getting others involved in the development. I think that's goes in a really good direction. Students love this. And now I'm looking forward to when you and Lasha can finish the cavern from one side to the other so that we can, you know, take the tour around and go see each other's places.
Yeah, that would be wonderful. I agree.
Okay, Steve, do you mean connection with our next presentation?
Ah, sure.
Right.
Yeah, I'm just leading into it. There you go.
Okay, I cannot see any other questions.
I was probably too ignorant, but does the person talks to you or explains what parts or the game?
Excuse me, I did not get the question. Could you repeat?
If the person you play talks like, oh, this is muon chamber or something.
No, not yet.
I mean, it's a quiet game.
Today it's a quiet game, yes. But it could be something interesting.
Or to have some explanatory text appearing.
Yes, yes, for sure. This is ongoing developments. And also people like to have characters that they can choose. Today is a default character, some character that was available easily. But it could also be possible to have some physicists inside, if people agree.
Yes, very nice. Okay, thank you, Pierre, and we wish you all the best for future developments, and we are looking forward to the final version. So now we are going to learn about development of web-based detector display application tracer for Atlas experiments. So Levan is from Georgian Technical University. If I pronounce your name correctly, I'm sorry if I'm not. Okay, so the floor is yours, and please explain to us the project.
Okay, sure. So I just shared my screen. Can you see my screen?
Yes.
Okay, perfect. So again, I'm Levan Khelashvili from Georgian Technical University. And today I present a group from Georgia called Nuclear Engineering Center of Georgia. It's a group of 12 persons actually working on different fields from geometry to programming and all stuff. And every animation and detector part you will see in my presentation today is actually taken from our applications. And you can interact with them and see them yourself. At the end of the presentation, I have a link and you can go and see it yourself. So, okay, let's start with few words about detector displays generally. So what's detector display? Detector display is application, a software that used to visualize detector, components of detector, events going on in the detector components, and general events that are within the detector. And these kind of applications are mostly used in the outreach, education, analytics, and engineering teams. So as I already said, these detector displays are used in many fields, and each field has its own requirements. For example, for the analysis teams, the application should be very useful, very informative, should display lots of information about tracks, jets, about detectors itself. It should also visualize lots of data and should display everything detailed. For education and outreach purposes, applications should be a little different type. For example, education and students don't need the data that analytics people will use. Like education people need more informative, interesting and intuitive application because it's more aimed to the students that are going to use application for the first time, and it should be very easy for them to use. Also for outreach, application should be very attractive because first view matters. Also innovative because they shouldn't be seeing the normal default two-dimensional web page. It will be boring. And of course, it should be fun. It should have lots of features, lots of funny animations, and so on. And general requirements to the application, because we have outreach and education here, is that application should be easy to use. Everyone should be able to use it. Doesn't matter if it's student, school student, physicist, or scientist. It should be easy to run because if we're talking about outreach, we should be using some technologies that everyone has hold to. For example, any device that people can use. And it should be easy to run because if you're telling student or school student to try this application, he shouldn't need to have lots of setups and stuff going on. So looking at all these requirements, we try to create application. We went to selecting the application type to what kind of application should we create to fit all these requirements. So we just went through all these requirements and choose the basic ones, the default ones, and that were most important. And first of all, again, because of the outreach, we could create a mobile application that could be downloadable. And nowadays, from the 2019 stats, there are 3.9 billion Android and iOS devices. So if we can create applications that runs on mobile device, we already have, 4 billion people already has access to our application. Also, because we have analytics data there, it would be great to make it cross-platform. So it could run on the Linux because people are using CentOS in the CERN and different kind of Linuxes. And normal users are using mostly Windows and macOS versions. So we just thought about what to take, and best fit was web application because web application is easy accessible. You need only to input link, and everyone has internet connection who has any device, mobile or a laptop. So we decided to go for the web application. And first thing about web application, if you're trying to create detector display, is that we didn't want two-dimensional display. We wanted three-dimensional display. So we found a great library called 3JS that is actually created by the team called Kronos that created OpenGL in the early 90s. There are lots of famous games written there like Quake and so on. And 3JS gave us opportunity to create web detector display application, a three-dimensional application in the two-dimensional space of the web application browser. Like everyone has browser. So first of all, looking at all these requirements, I'll go back again. We started developing one application called Tracer. Without any extra name, any additional names, it was just Tracer that was going for the outreach and education. And the whole part was to visualize fit every requirement, fulfill all of the requirements. And we're trying to make it innovative and fun and have tracks there and jets there and everything. And we kind of succeeded, but then we thought, why not create more? Why not improve? Why not upgrade it? So we had to create new structure for the application that would fit more and upgrade more and do everything better. So we came to conclusion where we needed more complex system. So we started developing engine for the application that would have basis of all the requirements we needed, the main requirements. For example, animations, interactions with the detector display, geometry loading, and all stuff. So we created a system that could handle additional inherited subsystems. For example, we could have one application named core. Nowadays, its name is tracer core. That would have all the main basic functionalities in it, and all the children systems like event display systems or tile colorimeter display systems or any new display would have all the functions and methods inherited in itself. So we didn't have to create new display every time, and we could just reuse all the features. Also, we have different stuff, resources, for example, events and geometries that we want to reuse and we are reusing now. So as you can see here, let me just mute my, okay. As you can see here, this is structure how it works. All the basic requirements are going in the core, and core is just split now, and even display and different applications are using core functionalities to target one main goal. For example, event display goes for event display and stuff. Okay, so this subsystem gave us potential to create lots of different displays. For example, if we will have new idea right now, we can just start developing by taking and cloning a core and just building new system on it. So, okay, let's go dive deeper and go for the core. Oh, 1 second. Oh. Okay, so what is so-called tracer core? Tracer core is JavaScript, vanilla JavaScript application that consists of over 6,000 plus JavaScript lines. And when I say JavaScript lines, I mean the vanilla JavaScript, because we wanted it to be very reusable. We don't want to break it with additional frameworks and additional stuff. And we were just using very minimal application structure like jQueries and 3GS. So it will not need to be rewritten and will be compatible to any additional upgrades or version change of the system. This current core exists over 20 different classes that contain over 70 functions that contain, as you see, the rotation functions. On the right side, you can see some bunch of the functions we have, like flying function, like geometry selection, and tons of fun and intuitive and interesting stuff that every subsystem has with it. Like if I will go in another application, I will also have this feature, and I will not need to re-implement it again and again. And this core is made so easy that, I mean, I would say that it's even easier than writing hello world in some programming language. On the left side, you can see the command inputs that I'm inputting, like this is tracer command that I'm inputting, and it will just rotate the detector, and that's it. The function that I just inputted will just rotate whole system. And now this function is implemented in all the subsystems we have. So you see geometries on the right side, and it was one of the most difficult part of developing this application. Getting this detector, this huge motor Atlas detector display geometry model in the web application. You know, web applications have their limits, and they have very limited resources. Not only web applications, but also 3GS has very, very limited resources. So we had to find this limitation and solve them, because first limitation we got to was loading full detector of the Atlas. Because when you load detector, it's over, I don't know, few million facets that instantly crash your application. So we have, as I mentioned, we have a big team, and one of the team is working especially for simplifying the geometry of the Atlas detector. So if you will simplify geometry too much, we'll get the result as you see down there on the third line. It will be very ugly detector, and if we'll just load the first line, this browser will crash. So we solve this problem by simplifying geometry hand by hand, and I can say every geometry in our application is handcrafted, so-called. And this way we achieve the great performance in the low specification computers. Like if you have MacBook, let's say 2014, you can run the application on the 60 FPS without any issues. And on the newer applications, it's like even better. So this is about finding golden line between requirements and possibilities of the application. So next problem was about the Boolean cut of the geometries. So not only we need to show the detector, but we can't like show this like hidden, right? We need to cut it. We need to go inside the detector and show the components, show the events. So normal Boolean cuts are actually the detector and there's a surface on it that should be Boolean cut. But using WebGL, we tried it and the Boolean cut wasn't covering the side of the cut. And this was a great problem because you just get the detector that has nothing in it and it's just transparent and there's like air. But actually there is a part of the detector component that is important. So actually again, the tracer geometry team did a great job and gave us this beautiful geometry that you see now. And now we're just reloading geometries and showing different geometries on every cut. So right now we have the one half cut in half, looking at the different parts of the detector by just combining these cuts and getting the different image of the application. So after solving these problems, we were able to go through and start creating other applications. And I'll now talk about other applications like tracer EVD. So this subsystem gave us possibility to create the better event display and better applications for different goals. For example, tracer event display is an application that is based on the tracer core and use all its functionalities, plus it has additional track detection like muons and stuff that users and scientists and analytics can see and interact with and use it for the analytics data. And right now it is actually used and we're just adding more and more file loading, filtering, and so on. So EVD is improving in the, its own way without like independently from the tracer core itself. And also receives all updates that tracer core is taking. So we also removed the additional animations that you actually saw on the first post and the second page of the presentation, because EVD is more for the analytics data and shows more of a analytics thing. And we saw that speed of the event loading was more important than just beautifying it. So we just removed the animations and now the application for the event detection and event interaction is much better and greater than the core one. So the another application is tracer tile calorimeter, TC, so-called. And this actually visualizes the events going on in the tile calorimeter cells and the layers from the normal XML data and different data. So we also took this application from the, built the application from the core of the application called tracer core. And it has all the features like selection. Now we can select cells here if we were able to select geometries in the core. And now we have all the features here. And this is used from some teams and is visualizing the tile calorimeter cells right now. And you can see it on the web page that is on the last page of the presentation. And also, I'll talk a little about our future goals. And it is actually virtual reality. As we have core actually ready and can start and handle any new application built on it. Like we can start VR application or whatever we want. So we said, why not? We already have the fly mode that you saw in the video. And we're planning to create the virtual reality Google headset, the Google Cardboard VR headsets, virtual reality applications that will be roller coaster-like or fly-like. So users will be able to fly through the detector, or they will have like roller coaster experience where they will be going through the detector and then they will be stopped and will be asked, where do you want to go and what you want to learn? So by the Bluetooth controller or the look gestures, they can manipulate the system and say, I want to hear more about this, I want to learn more about this, or now I want to go there and see this. So this is our future plans, the VR, as I see it's very popular right now. And also a few words about tracer framework. As you see, our subsystems and the cluster-like structure gave us possibility to create more and more applications. And we created the framework where all these applications are sharing the same resources. So if we are creating geometry for one models, for one application, this geometry is accessible all across the applications. For example, we can load core geometry in EVD, we can load EVD geometry in core and back and forth and everywhere. So when we'll go to the VR, we already have all the resources we need, all the functions, and we're just ready to start and build new applications and build new features and add everything. So also the core is built that way that if we'll add any new function in the core, all applications are getting this update, and they can just choose like implement this feature in EVD or Talcal or not. So yes, that's it from my side. Here's the promised link, and thanks for your attention.
Thank you very much. It's very impressive. I heard about this project and never saw it. So
okay, now it's time to see it, and you can start now actually.
Yes.
Mobile device even.
Okay. So do you have any questions? I will pay more attention now to the, okay, yes. Mayrin, please go ahead.
Hi, thanks Levan for the presentation. These things are really cool. I have a question to you and the Georgian team. I think the points you raised about ease of setup and ease of use is really important. So can the same phones and computers that students might already have that would be used for the tracer event display, for example, would they also be able to be used maybe with a Google Cardboard for the tracer VR and other augmented reality and virtual reality we heard from the Georgian team yesterday?
Actually, what I was talking about right now is that these applications that I talked about are perfectly accessible. For example, I can actually talk about other applications too. Just a minute. So here's all our applications we have at this moment. Some of them are under development. And most of the applications like core, EVD, tile colorimeter, and the VR will be accessible simply for any mobile device, any laptop, anywhere, anytime. And the augmented reality applications will be accessible for the mobile devices like Android and iOS, but not every device supports the augmented reality extension. So there are some very old specification devices under iOS 10, I would say. Maybe that's iPhone 5 and 5S. So everything after iPhone 6 and 6S will support these applications. And it's the same level about the Android devices. So about VR, yes, they will be totally able to use the normal, simple mobile phones that they already have in their pocket or in their hand, no matter where. And they'll be able to just put on the Google Cardboard that costs actually a few dollars and start and like run application with no extra steps.
That's great, thanks. I don't have an iPhone 6, but I know that some students might have.
Yeah.
So it's nice to know that they could already do it.
Yeah, we already tried it and tested it, and everything looks great on the iPhone and Android phones, especially for the AR part. And one of our applications, the AR application we're planning to be the web AR application. We're just, it's really in the very ideal level right now. We're just developing it, and we're trying to implement the augmented reality in the web at this moment. So let's see what we'll have, and maybe in the next presentation we'll have like web AR too. So yeah.
Okay, thanks very much.
Thank you for your question.
May I ask now, Miroslav?
Yes.
I just ran it quickly, and some event displays, and when I click on some track, it disappears. Is it okay?
Track disappears?
Yeah, like entire detector flies away.
Well, you just found a bug.
You see, you are on a roller coaster.
I mean, so the question is how much this is debugged. So can it
is,
go for master classes, for instance?
It can actually totally go. We just had the quick fixes on the end of like before presentation, and I think we just missed the bug right now. So it just presentation problem. So yeah, actually we're testing it pretty often. Like once a month, we have like few days serious testing of all applications, and we're just writing down all those bugs and just fixing them all the time. So yeah, this is the hot fix bug, I would say. The bug that caused the bug fix caused the bug. So yeah.
You simply, Levan, you simply ask Miro to find bugs for you.
We're always looking for bugs, and it's like probably application is the main goal for us. So yeah, finding bugs are good.
There is a question from Pedro. There is a question from Pedro. Pedro, please go ahead.
Thank you very much. Levan, I liked it very much, your presentation.
Thank you very much.
It sounds first a very bright idea to join people from different disciplines to make it quicker, the adaptation of geometry and the informatics. It's fantastic. I find that your testing, if you're going to test it in a masterclass, that will be a fantastic tool if you ask the students to find bugs, because usually there are many. They are usually resourceful in finding bugs. So you need to test a lot of different devices at the same time. Besides requesting Miros to do your debugging, that's also a good idea from Marjane. Now, I understand that you made these for the Atlas. Is that portable to other experiments easily, or would it require to redesign the frames?
No.
The coding?
So sorry, go on. Sorry.
No, and redo all the coding.
So yes, that's a part of the framework. That's the core. Actually, is independent from every system. Actually, this is called Atlas because it has Atlas geometries. If we will implement different geometries where our geometry team will work on it and simplify it, it will be any kind of display. It can even be like car display if we will want, if we'll just load the car in the system. So the Atlas is actually the name and the resources that we are using. So only thing that we will have to change is geometries, and I would say the event loading maybe a little. I'm not familiar with the event data of the other experiments like CMS. What do they store and how do they get data? So only things that we will need to change will be maybe the event loading and just geometries themselves. Nothing else. Everything else is perfectly working and running for every system.
Okay. Thank you very much. I believe that a suggestion to Marjane, and well, not to Marjane, to CMS people and to Atlas people, and LHC, Alice, of course, is to integrate these programs, also the proposal from Pierre just before, in the virtual visits. Because the virtual visits, if you get a glimpse of what you're going to see, and then you see the real thing, it would greatly experience the experience of the visitor.
Yes, you're right.
Absolutely. We have actually had I think yesterday Mariam had the presentation, and she actually said the Cognitive Festival. And we actually had the QR codes on the posters, and people were just scanning QR codes and just running applications super simply. So it's very easy to run web applications that way. No installation is required. You just put the QR anywhere, even on the flyer, and everyone has access to it. So yeah, that's a great point of the
thank you.
Also.
Okay, that looks like we don't have more questions. Thank you, everyone. Thank you, Levan, for great presentation.
Thank you for listening, and thanks for the feedbacks and questions, and fun for the bug.
So now we move into presentation by Peitsa. Peitsa, are you here?
Yes.
Yes. And
you can hear me, I guess I am.
So Peitsa is from Helsinki Institute of Physics from Finland, and will tell us about the CMS Open Data project, and in fact the feedback from Finnish teachers who received training in using programming resources to bring modern physics research into their teaching, if I'm saying correctly.
Something along those lines.
So we are looking forward to learn more.
Let's see if I can share my screen here. Do you see something?
Yes, we are seeing your screen, yes.
Okay, that's yeah. Okay, so before I start, I have to commend Levan for the absolutely amazing classification of requirements from the viewpoint of teachers and so on. I really like the ease of access thing. But on the subject of my talk, hello and welcome everyone from my part too. So in this talk, I'll be covering some hardships that we are currently facing in science education, what we have done about it at the CMS Open Data team, and how it has been received among teachers, mostly at high school level. So my name is Peitsa Veteli, and as said, I'm from Finland, and my background is in teaching physics. So this might be a bit more pedagogical than the technical bits many of you are probably more used to. And I got a thing for diverse contextual learning and scientific literacy as an educational goal in itself, trying to make sure as many students as possible would really just, find this joy of science and take curiosity with them, even if they aren't necessarily aiming for academic careers. So let's begin. The science education currently is in a bit of an ongoing crisis. Too many people, both young and old, see science as something that's not for them, which is of course wrong, but either they see it's boring, it's hard, it's detached from real life, or it's just plain irrelevant. This has been going on for decades and was studied most extensively in the large relevance of science education study about 10 years ago, where especially the developed countries showed signs that the students just weren't that keen on taking up natural sciences. Funnily enough, when they're kids, everyone starts curious, but as one goes further on in their school years, their interest seems to wane more and more. As ever with humans, the exact reasons are, of course, myriad and complex. Still, we can see some general themes, including things like increasingly stressful requirements, notions that science is hard compared to other subjects, or a simple lack of relation to everyday life. I mean, after all, we live in the 21st century and everyone is using their smartphones and stuff, so why do we have to learn calculus by hand or perform 17th century physics experiments with caveman technology? In the modern society, we also live in a deluge of information, and there is mounting evidence to believe that 25 years is soon the old 18 as far as maturity goes, while in many parts of the world, more and more important decisions about the rest of one's life are heaped on youngsters before they have actually even made it out of school, which in part often forces the curricula and teaching practices to tighten up towards final exams, which then stifles the time to do deep student-motivated inquiries and so on in a vicious cycle. And none of this is helped by the widely held caricatures of what scientists actually even do, besides just wearing white lab coats and exploding things. I mean, every one of us is wearing a white lab coat all the time, right? Based on that, it's not hard to see why one would ask the school system to change with the times, which is, of course, the thing that everyone asks it to do all the time, which means that, like your average social media commentators are experts on whatever they have just Wikipedia'd 5 minutes ago, so too it seems that we have all of these untapped brilliant minds all over the place just waiting for their chance to open the educational system with all of their newfangled ideas. Well, spoiler, it happens to be pretty damn hard. So just to start beyond the sheer inertia of existing institutions and conventions, we actually need to even specify what that change should actually be. To be better in line with the idea of representing actual research world in the classrooms, we need authentic practices. Last year, Anker Hansen and Andrei went through a lot of papers on the subject and summarized some of the most used meanings for authenticity, which in a nutshell usually means that instead of rote calculations and half-hearted demonstrations, it seems we need to be using open-ended inquiries, representative research methods, and contextualization in the students' lives. None of that is rocket science, but it's still really hard to implement in a system that has been just rolling on by its own momentum for centuries. And of course, we have to ask what's harder, learning a new language or coming to grips with the idea that when dropped, heavy things don't fall faster than light things, because every one of us carries a lot of misconceptions and intuitive thinking, which then hinders our abilities to rewire our brains to think in a more scientific manner, which is one of the things that makes teaching and learning science in its many forms, be it chemistry or physics or biology or whatever, that much harder. Of course, there are then other things like our brains not knowing the difference between a general law, what's a specific situation, how much we can deduce, and how much has to be taken on faith at different levels of knowledge, what can be construed with hands-on empirical evidence, and so on. And then there's, of course, the practical side, when we have to think about equipment issues, which are more pressing concern, as well as a pedagogical concern, because some schools might have equipment, some might not, some might have better, some might have some age-old little boxes of gum or whatever that they can use. And even if you have modern demonstration and research equipment in your school, they could still simply resemble magical boxes that have buttons, which from the pedagogical side is perhaps not the best when it can contribute to the fact that people think of science as something that's detached or too abstract or just plain weird, when instead of seeing something with your eyes, you have a box that goes ping. For an example, we have a modern physics lab, which is of course all last century stuff, where we have boxes with little wheels and pins and buttons and stuff like that, and then it gives you some numbers which many of the students at high school level just have to take on faith because they cannot really see anything going on in those experiments. Then to the main meat of this speech. For some years now, CMS has published its data openly on the internet, which has been used for both research and educational purposes. But here I want to especially highlight the open data education side and the work therein in the light of those themes previously brought up. Programming is currently the hot potato of the educational world, as digitalization is creeping into everywhere. In many places, this initial period has been quite chaotic, and often it has just been dumped on the teachers without much of a warning. Here in Finland, for an example, when the national curriculum changed to incorporate programming a couple of years back, it was just basically thrown on the mathematics teachers like, "Oi, you do numbers. Take this in addition to whatever you were already doing." The situation is somewhat better now, but the initial days were quite ugly. It's not too far-fetched to say that policies like this may contribute to these subjects feeling detached and uninteresting for many students, just like traditionally lamented science teaching has been when it isn't directed towards interesting phenomena and larger contexts that actually provide motivation to learn the basics. Instead, our team wants to provide teachers with free tools and materials that they can use as part of their teaching, so that there is more meaning and reason to learn how machines think, what one does with data as part of an actual research, rather than writing hello world as an after lesson and so on. So instead of simply putting all programming in schools to a distinct subject, we'd like it to be a part of other subjects, like you could use it on your physics classes or your math classes or whatever, just like you would use a textbook and a pen. It's just another tool in the modern toolkit. And the team that we have that has been doing this is a combination of acting physics researchers as well as students with pedagogical backgrounds, working in tandem with our teacher friends to constantly improve our materials based on their feedback. There are some links in the slide that you can go and peruse if you want to. We chose to use Python on Jupyter notebooks for this purpose because, as Levan said a moment ago, teachers especially have too much on their plate already. Requiring them to learn bespoke systems for singular topics is bad value for their time. Python, being both reasonably intuitive for beginners as well as being one of the most general and widely used languages on the planet, suits this purpose quite perfectly. Notebooks can be run on pretty much any platform, from smartphones to potatoes, and with sites like MyBinder or Google Colab, you don't even have to install anything. You to just have a gander of what's this thing about. This allows quick demonstrations as well as spontaneous exercises without much of a hassle when getting started. But of course, it's a good idea to install a quick Python environment on your machine if working for longer periods, because anyone with experience of classroom life can tell you that if something takes like half an hour to get set up, no one's going to use it, and it's just going to be thrown out the window before anyone actually even thinks about it. Our system is pretty much usable in a few minutes. You just open GitHub rep, you see what you want to do, just click open one of the binder links, and off you go. That's the quick and light version. Oh, actually, not yet that. On Python, being a generally General language and so on is a strength, because as much as we love to push our particle experiment data on the teachers, this project also has a larger purpose in mind, which is to show that pretty much any set of data can be analyzed with somewhat similar methods and thus help the students to increase their understanding and appreciation of the nature of scientific work. If particle physics, which is a rather narrow field among school subjects, isn't the hottest thing of the day, switching to another context like, say, astronomy or the hometown's medical statistics might be just a thing for some students to be hooked on while learning the same problem-solving skills that they would have working for, trying to hunt Higgs or something. As the materials we provide are full of open code and examples, they can be easily taken and modified by the teachers for their own style and purposes as they like. At the end of the day, what matters is that the students gain something for their efforts, be that new insight or a new blip on their radar for what they might like to do in their future careers. And then as to how we actually turn all of this lofty talk into practice, myself, Kati, and others have been organizing teacher training courses to get these methods into use at the grassroots level. After all, a motivated teacher can have a huge effect on their students over the years. These courses might happen as part of an international teacher program at CERN, or as a part of in-service training, as we have been doing here in Finland, or where we have a pretty active CERN network between high schools and universities, which is kind of like the bigger German network that was displayed yesterday. Some workshops have also been directly done with the students, but having an outsider conduct a short session with perhaps unfamiliar methods is always going to be something of a surface level scratch when you compare it to what you can get, what you can do with the familiar and safe teachers that they can work with for longer periods of time. So what's in a course then? Usually we have 2 full days of work with researchers, PhD students, and such stuff at hand to answer questions and chat with teachers in general. On the first day, they are given lectures on the standard model, accelerator physics, and such before we start browsing through the existing materials. They get to explore various datasets like hunting the Higgs or W bosons, visualize trajectory spectrums, not just fool around with other subjects like exploring the daily numbers and placement of sunspots or earthquakes that are published openly on other portals all over the internet. As much as I understand, our work is a bit more programming intensive than what you might find in various masterclasses, which takes a bit of time to get to take in and produces a reaction in the teachers, which we jokingly call shock and horror. While you could just throw some exercises in front of students and let them dabble with them as much as you like for a couple of hours, with teachers, you actually have to take time and make sure that they are on board with what they are doing if they are to take it as part of their routines. If they just feel that they are pushing buttons but gain no insight out of it, all has been for naught. Which is where the second day of the course comes in, as the attendees have now had a nice night of sleep and can ask questions, delve deeper into our materials, or start to come up with their own. For an example, some have taken a look at how stock markets have been doing, one made a notebook to compare snow heights at their hometown from the last 50 years, while another made a 3D map of bird migrations in the 80s and so on. With the basic idea being that whatever they like, they get to do, and of course, since many of the attendees come from our CERN network, what they are interested in this case, is particle physics, so they will be doing a lot of work with that. But for those that aren't, like an odd vocational teacher or someone else who has been sneaking into the course, they might have completely different motivations, which is fine, because we only want them to get inspired and start doing their own things. If they do it with our data, great. If they do it with something else, also great. So, the feedback.
5 minutes.
Okay, the feedback thus far has been almost universally positive. Most of the teachers liked our methods and materials, even if they weren't initially experienced with coding, and felt that such tools could help them with the perceived rift between the real world and school science. Most felt that they would like to use notebooks and such in their works, but I sadly don't currently have any real follow-up data because, come on, who answers their emails after events? Some other highlights from the feedback. Many were aware that open data was available, somewhere about some subjects, but they hadn't really considered that they could be using it for education. Most consider such data more authentic and interesting than your usual textbook example would be, which aligns pretty well with the literary consensus about motivating the context, even if the information content would be pretty much the same. Particularly for particle physics, teachers felt that this was finally a tangible way to interact with a subject that is often very abstract or hard to comprehend. With programming, the sheer scope of thousands upon thousands of data points becomes feasible, and analyzing them even rudimentarily becomes that much more intimate than just looking at a graph and taking it on faith. And across multiple courses, I'd like to bring up one often mentioned thing in the spirit of some discussions of yesterday, the possibility of exposing the students to what a scientist or a data analyst might do in their career, as well as giving them a feeling of self-efficacy. I can do this, I understand this, is an important point here. In the few students' workshops that I have run, I have also noticed that such an opportunity was especially good for girls, who might not have otherwise come into much of a contact with open code, unlike a small fraction of the boys through example video gaming and so forth might already have. Too often, they miss chances of even noticing that they might like coding because they just haven't tried it. So if we could incorporate tools like this into the general education, we could also give a chance for those people to slowly change the trend that coding, programming, and so forth is seen only as a manly career. As a quick side note, I had the pleasure of talking with Adam and their Firming Up course of a group of American teachers who were doing something quite similar. You can read some of those comments. I won't go deeply into them, which is basically the same that we have gotten out of our teachers. So they too would like to have the world, school activities resembling the real world more, and tools like this and open data is a thing that allows them perhaps to bring that more into fore. Wrong direction. This finding seems to align with the rest of the physics education field pretty nicely, especially concerning the use of openly available or real-world resources that link the school and societal life outside it. Doubly so in those cases where the students have to find datasets themselves and discussing how trustworthy they are, perhaps learning more about the institutions that provide them in the process. For particle physics, the brand of CERN and the various experiments therein is a good draw for ancillary motivations. And then there's, of course, the whole discussion about what's the purpose of school in general anyway, and what sort of people we want it to produce. Fostering appreciation for the methods and experts who do science, even in those students who will not then enroll into academic life, but might become future decision makers, politicians, or otherwise active members of society, is of critical importance as well. I feel analyzing data and finding how it can be presented as well as misrepresented can be an eye-opening experience for anyone, especially in this age of misinformation and half-truths. And for anyone curious, here are some PER papers that you might find enlightening, especially Dr. Mestre and Anke Hansen. Thank you for the attention, and don't hesitate to get in contact if something piqued your interest. If there are any questions, I would be more than happy to answer them. That's it, I guess.
Thank you, Peitsa. Wonderful job. And
I'm sorry if I talk too fast.
No, not a problem. And I see Pedro has a question. So Pedro, please go ahead.
Fire away.
Hello, hello, Peitsa. Thank you for your great talk. I don't want to monopolize all the questions, but basically I was very curious that you had implemented these trainings and these notebooks already, I suppose. Yes. So the question is, have the teachers used that? Have they come back with questions and help? And how have the students reacted? In what sense? Has that increased it? You started by saying that the interest in STEMs has decreased. Now, has this turned back with an increase in the interest of students?
And that's an interesting question. I would like to have some research funding on. Basically, the thing is that it's pretty hard to follow up what teachers are doing unless you kind of just walk up to them and ask, what are you doing in your school? I know of some university lectures that have started using these. Not lectures, but courses. And in those, the reaction has been pretty positive. in singular cases and workshops with the students, I know at least those who didn't actively hate coding saw this as quite interesting and inspirational, perhaps. For an example, one astronomy exercise that I used was of great interest to high schoolers. And in the moment, you can see as their eyes light up that this is something that's interesting. And when they get a histogram out of some easy programming exercise, you can see that they are quite in it. But as ever, more research is required to see if such a thing could be integrated into their teaching or their education, and then seeing if those results are positive or just more of the same.
Okay, thank you.
There is another question from Mayrin.
Hi, Peitsa. Thanks for this amazing work. I'd like to ask, what's next? What do you want to add, improve, do anything slightly differently? Because I imagine you don't want to stop here, right?
Well, we aren't really stopping in a sense that, as said, this is our aim is a general increase in the data handling skills. So this isn't restricted to any subject. This isn't restricted simply to a set of exercises. So basically our GitHub repository is a place where we can just dump more stuff every time we make it. And I'm currently trying to implement some sort of a website which would be more intuitive to use instead of just GitHub, because, well, GitHub isn't intuitive for anyone who isn't a programmer by heart. It's kind of too bare bones for that purpose. And then currently I'm trying to think about how we are going to carry out these workshops with the teachers in socially distanced manner, because this also is going to be different from everything before. But basically, if I had my ideal say about the thing, I would first organize the materials in such a manner that they are functional in the purpose as defined by the same rules that Levan presented earlier on. For those who have absolutely no experience whatsoever, take this. You who have coded before, check this. You who are interested in something else besides particle physics, check here, and so on. Which is basically what we are already doing, but I'd have to run it through hundreds and hundreds of other people so that they could actually give some feedback on how they should be organized. So just not my brain that's telling how it should go, because that's not what most of the people would like.
That's very interesting. Thank you.
Thank you.
Okay, do we have more questions? No, I don't see any. So fingers crossed for the future of the project, Peitsa, during coronavirus. And thank you for your presentation. So now we move into our last presentation before the break. So Pedro, do you think you can take a photo at the end of this presentation?
Yes, yes, of course.
Okay,
I
perfect.
can take a photo. So people beware, do not leave. So
yes,
you can
wait until the end
until Marjana tells you to leave, do not leave.
Yes, so now we will welcome Kate Shaw. Kate, are you here?
Hi, Marcella. Yep, up here.
Perfect. And Kate will tell us about Atlas Open Data.
Okay, I'll just get my slides. Okay, hi everybody. Yeah, so I'm Kate from the University of Sussex, and I'm going to be talking about the Atlas Experiments Open Data project with a bit of focus on our more recent 13 TV release. So this is on behalf of our outreach group at Atlas. And I also want to talk a little bit at the end about our journey, so what steps we took to develop this fully educational data set. Okay, so the Atlas experiment is dedicated to providing our data publicly. So what do we mean by publicly? Well, given the high level of what we do here, we've really had physics undergraduates, graduates and lecturers really in mind to access our data and to be able to do plots and analysis. However, we also want the general public and high school students to be able to use our data as well. So we've been providing proton-proton collision data collected by our experiment, and we've really done this within a comprehensive educational package. So what we're really focused on here is making sure that the data is usable, and it's usable at various levels depending on different students' computational and physics backgrounds. And we also wanted to make it usable for different educational objectives. So by way of an introduction, just to overview, so students get to analyse real LHC data themselves, and they get to search for particles, standard model particle, Higgs, or even new physics such as supersymmetric particles. So more advanced students get to use example code and framework so that they can use this to really learn various analysis techniques and look to understand things about statistics and how uncertainties work. But then also for less experienced students, we provided tools so that they can access the data without the need for coding, so that they can, for students and for the public, so that they can start to understand things about histogramming and how we look at our data without the need for coding. And we also provide introductory notebooks to give students a kind of stepping in format for basic coding and analysis training. So our collision data, of course, is released with Monte Carlo simulations and a bunch of analysis examples. So all the way back in 2016, this is when we released one inverse femtobarn of 8 TV collision data. And earlier this year, we released 13 TV collision data, and this was 10 inverse femtobarns. And along with the second release, we also released a lot more beyond the standard model Monte Carlo simulations, so that students can really do searches for new physics as well as reconstruct Higgs and standard model particles. And we added many, many new analyses. So all of the data sets and the Monte Carlo is available on the Open Data portal. It's also available on our website, which I'll talk about in a couple of slides. So along with this data set, we've provided analysis examples, both in C++ and in Python, and various options to access the data and tools. And this is using Jupyter notebooks and virtual machines. So as I said, we really wanted to look at different educational objectives. So of course, one of the key ways you can use open data is for advanced training in experimental particle physics techniques, learn about particle physics, Atlas, etc. But we also want to make sure that the open data can be used for workshops looking at programming using C++ and Python, so that you can use the open data as an example to learn basic programming skills. You can also use it just to ease less experienced students into the ideas, basic principles in particle physics, basic uses of root and how histograms are organized. And then of course it can be used for understanding of big data and for more advanced training such as machine learning. So here is our documentation for the 13 TV. You can access our website from this link. So on this documentation, we have, of course, all our 13 TV data sets and Monte Carlo simulations. We have all the physics analysis examples. The analysis framework is given, and then we have the Jupyter notebooks and virtual machines and data visualization. So I'll simply go through a few of those tools in the coming slides. So this is our data visualization. It's called our histogram analyzer. So the point of this is so that, again, general public, high school students, or anyone without a strong background in coding can actually access our data and understand a little bit about how we do particle physics without the need for coding. So this is really perfect for beginners. We have two analyzers available, one on 8 TeV and a slightly more advanced one for 13 TeV. So you can see from this little GIF at the side, the idea is that we have all these selection of histograms with various variables. And then we have the different samples shown in the bottom right. So you've got Higgs WW, and then standard model WW, TT bar, and Z. And so by analyzing this data and looking at what cuts to make, you can look at optimizing certain signals over others. And of course, one of the key things to do with this is to see if students can find the Higgs. Okay, so this is just overviewing some of our tools. So with our analysis framework, we really wanted to do it both in C++ and with Python, because different students will be looking at learning C++ or Python for different courses. And for Python, we use both of uproot-based framework and we use a pyroot-based framework. And so how can you use this? So we have 3 different options. Again, this is dependent on different students with different resources, different schools, and what sort of computational skills they have. So the sort of most simple way to do it, but you need to be really working with the Atlas physicist, is to download everything and run it on your laptop. But you need to have lots of software and tools such as root installed. So a second option that we have is the virtual machine. So the virtual machine can be downloaded onto your laptop, and then it has all the tools and everything you need within that. So that makes it much easier for people to use without having to have more knowledge of how to use root, etc. And then the third option is the Jupyter Notebook. So these are fully online. Example there is given on the right. So you have all the coding in there. And as you execute it, it can do your analysis. So there's a diphoton invariant mass for a Higgs analysis showed there on the right. So we also wanted to develop some physics analysis examples so that students could maybe do their analysis and compare it to Atlas results. So we made 12 of these. These include standard model, including single top, TT bar, W and Z bosons. We have some Higgs searches in diboson and gamma gamma. And we've also been developing beyond the saddle model searches. And these include SUSY and Z prime. So here's just an example for the Higgs to gamma gamma. So on the left, you can see at the top, this is a paper for the Higgs to gamma gamma with 36 inverse femtobarns. So we take a simplified selection for the event selection for the histogram. At the bottom, showing the figures that the paper produced. And on the right shows what we get from the analysis framework when we use the open data. And this is for just 10 inverse femtobarns. But there you can see the nice peak for the Higgs. Okay, so how is the Atlas Open Data used? So it's really been used since 2016 in a lot of different universities in a lot of different countries all over the world. They've mainly been using it to integrate it into lab courses, and they're also used for bachelor's and master projects. They've also been used to run international workshops in schools all over the world and to train undergraduates really in physics analysis, machine learning, coding and big data. And you can see just here on the right, so this is our educational website, and you can see we've had almost 6,000 visits over the last year. You can see a little bit of a drop when it's been the holidays, a bit of a peak when we had our new 13 TeV release, and again, a bit of a drop during the COVID lockdown period. So I want to talk a bit about how we developed the open data idea. So of course, we all know it's very important that any publicly funded experiment should release the data, but we really need to think about how we wanted to do that. And as I said in the introduction, we really wanted to work out how it could be useful and actually be used by a wide variety of different types of students. So along with the data sets that we released in the Monte Carlo, we really gave a huge effort into developing educational resources and really thinking about the different levels of physics knowledge, of computational skills that different selections of students would have. So we wanted the more advanced selection of university students to do high-level physics, actually do similar analyses that we do on Atlas. We give them an option of resources depending on their computational skills and the resources they have at their university. And then we also, as I said, developed this kind of more introductory level for beginners to start analyzing data without having the code, such as the histogram analyzer that I already showed you. And we developed a bunch of workbooks that would ease them into some basic coding and how to make histograms. So we work with a lot of different students at different levels in this development. And we really wanted them to be part of our team to really test what we were doing, to see if it was at the right level. And they really worked with us to improve. So the Atlas Open Data isn't just really from just the Atlas collaboration, from our outreach group. It's from this variety of different students, high school students and master students that really given a lot of input into this program. So just to show you some of the students we worked with. So we worked with high school students and undergrad students when we wanted to do the writing and then the testing of the analysis frameworks and the notebooks. So you can see a nice picture on the right here. So these are 3 high school students that came for a short time during the summer, and they spent their time developing notebooks and testing them and seeing what worked, what they didn't understand, what maybe we needed to include more of the more words into our glossary, etc. And we think this is a really nice program. Not only do they get to work with real data, and learn about Atlas, learn about particle physics, but they get to contribute to a program and write notebooks that get used all over the world by students. So along with the high school students, we also work with students at ICHEP and at CERN, and we also, of course, are integrated with the summer student program at CERN. So almost every year we get a summer student that again comes and works with us for the summer and develops and tests these notebooks. We also run workshops all over the world with lots of international people. So this is important to be doing this worldwide, because we don't want the resources to only be useful if you're in a very nice, well-funded university with lots of nice computational, with lots of people that can help you that have high computational skills, etc. So these workshops run in lots of different countries have really helped us to understand what would work and what wouldn't work, technically, as well as just the physics. Also the level, so was the level appropriate for the students? And then a lot of validation would go on. So this was really useful to improve and test all the notebooks and the frameworks that we used. One of the key things we did develop is to put everything onto a USB key. So in some countries, they don't have access to a large bandwidth over the internet. And so if you can't download the data and the tools, you can't do anything and you lack access. So to make sure that students, no matter what country you're from, have access to this, we also have developed this USB key that has the virtual machine and all the data, Monte Carlo on it. And we send it out to any university that wants to use it. So I've just listed here some of the different workshops we've done at ICHEP, at CERN, and in a bunch of different programs over the world, very much focused actually in Latin America. And then we've been working also with master students. So this is working with Atlas collaborators who supervise a master student and have decided to do it on the Open Data project. So this is a much more advanced contribution. They've written their master thesis to either develop a physics analysis or create a brand new physics analysis. So here again are a list of some of the master students that did their thesis on the Open Data, and there are many more. And we've also been doing a smaller project with their bachelors for their final year project. Additionally, we've made a qualification task on Atlas in outreach so that students can spend their qualification time in the first year of their PhD working in our team. And we've had 2 students, PhD students, do this so far, and they did the full development of the 13 TV dataset. So as I said, this is really a great way to get students to learn about particle physics and analysis techniques, get their hands on the data without needing to learn the full Atlas software. And of course, they get to contribute to a project, create a notebook that will go into our program and be used worldwide. So this is my final slide. The Atlas Open Data is being used for educational purposes all over the world. We're currently working on video tutorials to assist non-Atlas members to use our open data. So these tutorials, you can see a couple of screenshots there on the right. They're really there to be linked from our documentation so that people can see in real time how to do the analysis. Also to just be used as standalone to coach new people in over the YouTube channel to see what we're doing and see if we can draw them into the site and download the data. So we're making these multimedia videos. It's very, of course, vital for online learning. It's also very useful for instructors. So even an Atlas physicist or any instructor that's running a course or a workshop using open data, instead of having to describe and learn everything themselves, they can do some of the introduction and then bring in these videos to help the students, and the students can then watch them again to follow the instructions. So we're really hoping to use this open data to reach out to more people and to bring Atlas physics really to their homes, to outreach the idea of Atlas and particle physics, and really hopefully to inspire many more people, especially young people, into physics. Okay, so thanks very much for listening to me. And yeah, I'm happy to take any questions.
Thank you, Kate. Impressive and a great idea to involve students into working on open data. Do we have any questions?
Yeah, I'd like to ask some.
Okay, yes, please go ahead, Peitsa.
Okay, first off, thank you, Kate, for this nice presentation. And it's always a pleasure to see others doing their, using their open data in such constructive manners. I would like to ask you about how did you, as you said, that you have materials that are aimed for people who really aren't that much into programming, but you still said that you use root. How have you, say, well, not perhaps simplified, but integrated root into those exercises so that people who don't have lots of programming experience can still actually get some sense out of it, because it isn't the easiest language for that purpose?
Yeah, so if you use the C++ physics analysis examples, you do need to have some understanding of root. I should say in the examples in Jupyter Notebooks, we give a lot of examples so the coding is there. So it's a way of students being able to run it and maybe be taught line by line what the code is doing, but don't necessarily have to do it themselves. But then we have developed things in Python that don't need knowledge of root. And I think this is something we thought about for the education objective of not necessarily becoming an Atlas physicist where you need root, you need C++. If it's for the purpose of just understanding more about particle physics, then you can use the Python-based frameworks, and they don't have a dependence on root.
But is it still there running on the background?
So there's, we have pyroot and uproot, and both of those are different ways of interacting with root, yes.
Yes, thank you.
Pedro?
Great, thank you very much for another great talk. Now, you showed two slides, the information on two slides, which struck me somehow. The first was on you said that in Latin American during 5 years, or during 4 years, you had 1,000 students.
Yes.
That's so that's when you had your whole life in Latin America? How did you manage? How many workshops per year, or each workshop was with 200 students?
Yes, so this is with the Physics Without Frontiers program that I run at ICHEP, and this is working with a group of, I think they're mostly Atlas physicists, and they're from Latin America. Okay. And they run a program there every year where they visit various different countries. So this is all includes places like Venezuela, Colombia, it's been to Peru, Argentina, and Uruguay, many others. And then it's done every year. So,
and these students is university students or high school students?
These are university students.
Okay.
So during each of these events, they do also outreach events with high school students, but not with the open data.
Okay, the other remark I believe is in slide 9, where you show a graph of the evolution of the access to educational site in recent times. And in pandemic, you show a decrease.
Yeah.
Now, for that thing also happened yesterday in some of the talks, and it struck me as well, that all these virtual activities should have a great increase due to the pandemic, not a decrease. But here, the other one was more related to virtual visits, so it would require people to go to CERN. Now, in this case, do you have an idea why there is the decrease due to the pandemic?
Well, I can't say for sure because we haven't analysed who it is that's been visiting our site. In general, a lot of people will be university students working at universities and lab courses. So I'm not sure, we don't know why, if they've been doing the lab course now it's been less accessed. But that's one of the reasons why we decided to do these video tutorials, because under a lockdown, of course, is a perfect time to be doing more virtual activities. Atlas Open Data is completely online. You don't need to be in a university or be anywhere. So we thought making these video tutorials, first of all, when we put them out on YouTube, would be a great way of bringing in new members of the public, hopefully maybe over the summer inspiring young high school students to, do something with physics over the holidays. So that's what we're trying to do to address it. But yeah, I mean, it's not, we're not completely sure exactly why the rate has dropped so much.
Okay, thank you.
Thank you.
There is a question from Antonella. Antonella, please go ahead. Yes?
In secondary school, I can tell you that during the pandemic, people would have had other priorities in school. So not all the schools could go online straight away, access to IT kind of computers at home. So that could explain some of the effects. So as a follow-up to that, I wonder whether you are planning to monitor what the situation might be at the start of the new academic year, school year, sorry. Secondary school children and also for university students, given that more adjustments would have been made for blended teaching and the likes. Thank you.
Thanks. Yeah, that's something that I think it would be a good idea to interact with people with. We've been contacted already by a few Atlas collaborators who are lecturing at universities, who see this as a very clear way of being able to run a lab course for something done remotely, since many universities won't be going back face-to-face in September. But I haven't thought about, or we haven't really discussed if there's a way we can do something with a high school. Perhaps that's something that we and other members of our community can think about and see if we can get in touch and see if it's something they would be interested in. Because as an online course, I think with all the documentation, it should be something that's not too difficult for students to go through on their own, and then have weekly interaction sessions for questions. So thank you for that comment.
Okay, so I believe that's it. Thank you, Kate.
Sorry, Martina,
please.
Oh
no, the Spina. Sorry, the Spina. Please go ahead.
Yeah, just a quick question. These students who came and they developed something using notebooks, did they have prior knowledge of the tools, or you taught them?
In general, they had, let's see, for high school students, they would have had zero knowledge of the tools. Right, okay. For when we've had undergraduates come, again, they would have had probably zero. Master students may have had some, well, will have had some understanding of coding, etc. But that's why it's a kind of a good program, because they learn a lot, they get a lot from the program. And of course, it allows us to make sure that, we get these notebooks tested and at the right level.
Okay, thanks.
Okay, so no more questions. So I propose everyone will turn a camera on, and Pedro will take a beautiful screenshot. So let's wait for everyone. Steve, yes. And we still have Sasha, are you here? Sasha?
I think that is his video. He's just staying really still.
Okay. And Pierre? Do we have Pierre? No.
Well, we have 27 pictures and we have 27 participants. So it looks to me.
It's okay? Okay, because I see
1, 2, 3, 4, 5, now 22. We have 22 pictures.
Okay.
So you're missing 5 people. Maybe they don't want to be in the picture.
No, probably they are away from the computer.
Okay.
So they don't hear us. Okay,
not.
so let's go ahead. Are you ready, Pedro? Should we wave and smile?
I'll tell you when to smile because I have to adjust the frame of the of what to be taken in the screen capture. And now I'll tell. Okay, 5, 4.
Okay.
Just smile
so
now.
Do we want do you want us to wave?
That was it. No, that was it.
Oh no! We have to smile. No.
You better do another.
I was counting down. Oh, now we have
no,
more
once again. At least we smile, okay?
Do you have a video of Sarah as your background? Marin is asking Sarah. So now let me take again the picture. Probably the frame is already defined, so much the better. So now keep smiling for 5 seconds.
That's hard.
Hopefully this was a nice picture. Yes.
Okay. Okay. So it means
I'll post it on the chat window or on the Mattermost because
yes, perfect. Thank you, Pedro. Thank you. Okay, so we let's take a break and we meet again 20 past. That was the plan. Mira?
Yeah, I would move it to 30 as yesterday. No?
Okay. Okay, so we meet 1/2 past because it's nearly 15 past.
Okay, see you then.
See you then. Hello.
Hello there, Martina. Do you want me to share my slides?
Oh, yes, because it's you now.
I guess it's me again, but then you'll be done with me.
Really?
Yeah. Well, I guess never.
Well, let's not be done with Steve, please. Not at least for the next 3 years.
Okay, I'll try to stick around.
Okay, so shall we start? Okay, so Steve will tell us how students from across the US are invited to CERN and are invited to take part in research at CERN, yes? And this is thanks to the University of Michigan. Yes?
So yep, exactly, Martin. Well, you've just given the talk. I can field questions now.
So we can
actually, this is a hat that I'm not usually wearing when you see me. So I usually have my Atlas hat on, or my blue Atlas hat, or my magenta iPod hat. Now I have a different colored blue Michigan hat. So you might ask a question already from my first slide. Is that what is a guy from University of Melbourne doing presenting the University of Michigan program? The truth is I worked for the University of Michigan for a very long time. I was a student there. And when I started working on the LHC, it was with the University of Michigan in 1998. And we started this program shortly after that. So I'm going to tell you about bringing students over during the semester, in addition to the summer. So the motivation in the US to me is quite obvious. We do not have a lot of students who have research experience. They actually have been in to see what it's like to work on particle physics projects, to actually build things, to do analysis with teams. We don't have a lot of students there with international experience, and there is demand for that. There's demand not just in our field, but also outside of it in the business world. People would like to find people who have had international experience, and Americans don't get out enough, and you can see that from other things too. CERN obviously is an obvious place to go. It's our premier place for particle physics in the world these days, for high energy research, and it is about as international as one can get. The University of Michigan began this game. I'll tell you a little bit about the history shortly, but back in 2001 with what's called an NSF, the National Science Foundation funds research experience for undergraduates, REU programs. I'll give a quiz on acronyms afterwards. And this started for us in 2001. We started to bring summer students over. And we also have one of the largest US teams active in the LHC, perhaps the largest. So we have a large team over here, but that's where we're not the only ones who are taking care of the students. I'm getting ahead of myself there. Why do we do this during the semester? In the summer, we have roughly 300 students who apply for our 15 slots that we're allowed in the CERN program. We're in the non-member state program for the summer students. It's extremely popular and very, very successful. There's also some students who have other things they have to do during the summer. Some work then to make money to fund their studies. And others have other activities that they need to do during the summer. And some just have a semester that they can take off, or they might have research requirements to fulfill. We have found, I'll show you why, but a 3-month program, it's an extra month beyond a summer program, gives you a much more in-depth research experience. It's really close to double the amount of time because there's always a ramp-up period at the very beginning for the students. And summer students spend some time in the lectures, which are fantastic, but they really don't have as much time to dedicate to research. There's a bit of the history. A lot of important people were involved in this. The agreement really started with Professor Homer Neal, who was my professor for a long time. He spoke with the Director General, Chris Llewellyn-Smith. He also, I didn't put up a picture, but Steve Roycroft, who is from Northeastern University, was also involved in the early days with this. They were asked a very pointed question, which was, why aren't all the American institutes jumping on board for the LHC now that the SSC is out of business? And one of the things that was brought up by them was that, hey, you know, it's far away. We don't have the opportunity to just take some undergraduate students, put them in my car and bring them over to help me for a weekend, or you know, doing some research, plugging in and checking cables and learning how to install electronics. And that's extremely valuable. Whereas, you know, the students in Europe could all just come into the summer student program and really get involved in research. The answer from the Director General was, well, you know, it's about money. The member states, they provide funding. And so this is part of, you know, it's funded by them. And Professor Neal, who was very, very bright and strategic thinking person, said, oh, it's just money then. And so he went to the NSF and got some money. That's the long story, but that's how it started. We found very quickly there were far too many students. There's a lot of demand from the students. There's also a lot of demand from researchers to have students. Undergraduate students are extremely valuable. They actually do things which are quite useful and helpful. And so we did a study to see, hey, would it be worthwhile to bring them over with a semester? A lot of very important players were involved in this. Professor Neal wouldn't do it any other way. He was an interim president for our university and sat on boards, on many boards of directors, including Ford Motor Company, Smithsonian, et cetera. So he always hit the nail with a very big hammer. So he talked to people. We brought together people from the NSF, the Department of Energy, the American Physical Society, even accountants to tell us how we would fund something like this. And after a year-long study, it was clear there was unanimous agreement that we should do a program. Only concerns were whether the students would be set back by this time, if that would have an effect on their studies. And I'll tell you the results of what we've learned from that. We did a pilot project. It was for a year. It was funded by the Lounsbury Foundation, the Richard Lounsbury Foundation, another board that Homer Neal sat on. He recused himself from the project at that point because he was on the board of directors. Lounsbury saw that it was very successful after a year, and they funded us through to 2019. Now, it's unfortunate we can't keep them. They like to start big projects, but they do not fund continually, so we don't have that funding anymore. But in the meantime, this isn't necessarily good news here. You see the word endowment. Homer Neal died a couple years ago. And he left money so we could bring students over, continue that program. It was something that was very dear to his heart. And in addition, we've started a partnership with the Permanent Mission to the International Organizations in Geneva. Just by hazard, they came to visit CERN, and I mentioned the program, and they thought it'd be a great idea to try to bring over some diverse students into the program. The students who come into the program, they're selected from around the US. With our current funding, they're from the University of Michigan, half of them. The other half, who must be from underrepresented groups, come from all around the country. And we look for large universities, small universities, et cetera, to do that. We make announcements in many areas, as you'd expect, and we judge them by their grades, recommendation letters, essays, et cetera. And we look for people not just who have the best grades, but who really have good potential. You can see a huge number of schools that we've gotten from a huge variety, from big universities in California to the College of St. Scholastica, a very small college located in Minnesota. Big variety. University of Puerto Rico has also been providing quite a few students. We do this 2 semesters. It's typically, I should call them trimesters actually, it's 3 months. They go from mid-September to mid-December, or from mid-January to mid-April. And I say or so because sometimes that gets prolonged. People want to keep their students. If students don't have to get back for any particular reason, we try to find ways to fund them to go on longer, or whoever they're working with will find some funding for them to keep them. Their timetable is something like this. We select the students and we get projects, proposals from different mentors. We map between the two. We suggest projects to students. They get to make some selection in there. We prepare everything. There's a lot of different things to prepare, from visas to paperwork, et cetera. When they arrive, we go and welcome them at the airport. I know a lot of people say that we're spoiling them by doing that. They should find their way to CERN. Many summer students do. We find it nicer to go and meet them, help them out, bring them over. A lot of these students, they come with a brand new passport. They've never been out of the country. And so it's rather important that we take care of them early on. We introduce them to their mentors, their research teams. They have project presentations that they do. They have 3 in total. They also have visits to the facilities, whatever we can arrange. They often travel. Sometimes we've helped them to go to different places. We've provided funding, for example, for a trip to Bern where they can go see the Einstein House and things like this. They give formal final presentations, a little bit longer than the other presentations. They get dressed up. We take them out to dinner, find out what was good and what was bad about the program, and then wish them well. And we also, you know, we listen to them basically. The experiments they work on is a huge variety. The main accelerators that are providing the projects is the LHC, and also the accelerator, the antimatter decelerator or antiproton decelerator. They're embedded in teams, any research team that has a good mentor. We choose the mentors who have important projects that are interesting for them. Mentors who typically perhaps miss teaching. Maybe they're just off on a year-end sabbatical, or they or are at CERN doing research and they used to teach. They have a good pedagogical capabilities and present real challenges for the students. And they do a huge variety. Anything you can imagine, they work on. There's a list of our last 2 groups of projects I just put up there to give you an idea that it's a huge variety, and they're very excited. Whatever they're working on, whether they're doing hardware, software, physics analysis, some of them are doing theory, and it's very impressive. Here's some images from their project presentations. We do one early on to just sort of make sure they know what they're doing, that they're on the right track. I like to work on their teaching abilities, how to say concisely and precisely what they're doing, fit in the big picture. I'm working on an experiment that's trying to find dark matter, for example, or something like this, before they go into the details of their projects. And we have them all together, which is very cool. It's probably the only place at CERN where you can find this. We get to spy on each other's experiments. So we get to hear what's going on in the different experiments. We make sure that they check with their advisors that what they're saying is not secret, but it gives everyone a chance to profit from what everyone's doing. So they learn all about the different experiments and the different projects that people are doing. So I won't go into details here, but we do record the last one, which is nice because they often put the links in their CV or in their application forms, and that looks very nice. They always do a very good job. I'm always very impressed by their presentations. They stay in Saint-Genis. They get, as I mentioned, they get visas. They're registered officially as CERN users, and I think that's really nice. They get put on the official mailing lists, so they know when there are different seminars or things like this going on. They really are researchers at CERN, and I think that's I think that is very important. Just not just psychologically, but it teaches them what it's like to be here as a researcher. There's a lot of paperwork you have to do. 5 minutes, that's fine. There's a lot of paperwork you have to do. We made, after about 4 years back and forth in negotiations between legal teams, we have an arrangement now where I can actually sign the form for them to be on the different experiments. It's a bit tricky, but since we provide the payment and the insurance and all, it was rather important that I do that. And as I said, they have enough money to live, which is something. It's not easy to do in Geneva, but they stay in Saint-Genis. They hop on a bus. We usually get them bus passes, and yeah, the apartments are not bad. They're not bad, so they're okay with that. And we also make sure they're covered with a health plan, and that's been used. I'm here as the local coordinator. You've got to have someone who's local. You've got to be able to translate, take them to see doctors. Kids get sick. Kids break bones playing games, etc. I won't go into all the details, but you have to take care of them. They travel around. They do a lot of, you can see smiling faces. They visit lots of places because you can get anywhere easily from Geneva. Occasionally we've had French courses, and they like that just to learn how to speak. And sometimes we get Sarah to teach them, our LHC communicator, teaches them a short course in communication as well. And I also teach them a little bit about education and outreach. They're stuck with me. The lessons learned, the benefits to the students, really, it's a great research experience. They're all thrilled by it. I've never had anybody say, I want to go home early, that's for sure. The collaborations get sometimes there are some mentors who have been passing on the baton from one student to another on a specific project. I think that our undergraduate students have been installing annealing for chips for upgrades for 3 or 4 years now, one from the other. And so doing real stuff that's real contributions to the experiments. Finally, the big question was whether this affects their studies. It doesn't. If they need to finish some course, there's something that's elective or something they need to get done, they can do that while they're here, and some of them do that. They take online courses. I can proctor their exams. Most of these students are very bright and can take off a semester. Others who do get set behind by a year have no problem with it. They're very happy to have this on their CV and on their registration form that they've been to CERN during research. We did an independent evaluation of this, taking surveys of all the students. This came out with the following statement: its impact on students is demonstrable, positive, productive, and extensive. A semester-long experience does not have any of the negative impacts that some have feared, such as interrupting normal progress toward a 4-year timeline to get a degree. The knowledge and insights gained in that semester greatly increase students' understanding of what a career in physics might entail. This is a view shared by both students, participants, and their advisors. One last bit here, I want to mention that the COVID effect, I should say, of course, we only got 2 months in this year, and we had to say goodbye to everybody. That was kind of sad. They were very sad to go home. And we don't know when we're going to start up again. Hopefully, I suspect it might not be till fall of next year, but we will see how that goes. The project funding, as I mentioned, 3 to 4 students come from Michigan, 3 to 4 from the State Department. You can see an image of us there at the State Department. They've been fantastic. They invite the students over for a lunch and talk to them and tell them about different opportunities they could get as researchers working at the State Department, for example. And I think that's good for them to be exposed to. We've really focused on bringing in young women and people who are underrepresented, which are typically people of color. Or Black people, or whatever, anybody that we can bring, or I'm trying to get some indigenous people as well, if it's possible. So in the future, we're really going to look for other sponsors. I have some ideas on how to try to focus a little bit more on this underrepresentation and try to get sponsorship from specific groups that are trying to get young students to get more involved. And I think, I will just leave here. I'm not going to read all of these quotes. They'll break my heart. I love what they all say. The students, the quotes in gray are all from students. The quote in blue is from one of our best mentors. And he was just thrilled to have the students there. And they've all succeeded, many of them receiving rewards. And I see students all the time from this program who are achieving a lot in careers, and I see them at CERN from time to time. I think that's it. That's my conclusions. Let's see, Andrei has a raised hand.
Hi, I just want to support. It's a great program. We had a student at Hopkins who actually went through and actually worked with us, so it's a good experience. The problem is that since then I was never able to kind of encourage other students to do this because logistics is difficult. You have to leave a semester, it's hard to plan in advance. Plus, I'm not sure, do they have to register at the university while they're there? It means their parents have to pay for their tuition, all of this while they're at CERN. So all those logistical things are kind of complicated.
Yeah, there are some things that we can't provide a solution for. In other words, with their own university, they have to negotiate and see, can I take a semester off? And if it's someone who's getting support already for their studies, they can often get support during that time for this. That has happened a few times. We don't make them register at University of Michigan, but often they can get an agreement to get credit. So students get credits for doing the research. but we can't solve all the issues. If a university doesn't want to do it, want them to do it, then that's one thing. Usually universities have been quite supportive of the program and have said they can take this semester off. It's not a problem. But I don't know if Johns Hopkins or if another school has difficulty with it. We
are very supportive, but just sometimes those issues they cannot solve. So.
Yeah.
That's great.
I see Pedro has a hand up.
It is a great program, certainly. But what I wonder is, coming from the question from Andrei, is it would seem to me so obvious that for the university would be a surplus to have the student go out for a semester and coming back with learning things for the university. So it could have it at two ways. First way, not pay a semester tuition fee, and the student would do the semester, would just delay a semester. Or second wise, would pay the semester normal tuition fee, but then it would be like an Erasmus program in Europe. In Europe, basically all universities do have this Erasmus program where the student gets out of the university for 6 months or for 3 months, for one semester.
Yeah.
Of course, it's supposedly to do disciplines in other university and come back with credits, but the grades, marks, and so on. Now, 3 months at CERN is so much greater than any other 5 disciplines in another university, to me, to my mind. What they learn is so much better for their CV that this could be, I think, bargained with the universities in the US, especially because then the student goes back to university with so much more learned knowledge that the university should actually encourage students to do it.
Yeah, I mean, I'm obviously, I agree with you. I think it's the experience is so good that they should jump on getting their students to come. And a lot of the small schools do that. They seem to be happy with it. We're getting a lot of small schools students applying. And so I think that I should ask all the students, they're different. I did at one point ask them informally at a dinner, who had to pay for the semester, but most of them had it off. They were able to take a sort of a sabbatical for a semester. So yeah, I agree with you. Now, one of the things that did get set up was that we had the president of the University of Michigan and the president of the University of Geneva sign an agreement at the beginning, so that if a student wanted to enroll at the University of Geneva and take a course, because there was some course they needed to take during that time, that they could get credit for it at the University of Michigan, and which then would be easy to transfer. Most universities could then transfer that within the US. So it's just sort of making that bridge over the ocean.
But the University of Michigan would accept credits done by CERN? I mean, if CERN gives a certificate.
No, this is by the University of Geneva.
No, but the point is, for example, now we are preparing our whole we are redesigning our programs at our university, and we actually have implemented some credits for internships. And internships at CERN will be credited in the university system.
Okay.
We just need a certificate. Somebody of, let's say, guaranteeing that the student was not on vacation all the time.
And then they get a certain number of credits for that.
And then they get a certain number of credits for that.
Yeah.
Which is, in the case of the full internship at CERN for 3 months, it's not really adjusted to the amount of work carried out, because it's only 6 credits, only equivalent to 1 discipline, whereas a term should be equivalent to 5 disciplines.
Yeah. No, I understand that they have to work out those details. And this has certainly happened with several of our students, that I think if their program already had that possibility of doing research, and it would be at the university typically to get some credits, and that sometimes that can be even required, then this fulfilled it. They would do something here, they might have to write another paper or something like that, and it fulfilled it. So essentially it's like that. I don't know if that it's true for the University of Michigan? I think so. I can ask the students next time I see them if they get credit.
Steve, there is one more question in the Mattermost.
Okay. And Mattermost, okay. Can you?
Julia, she's probably watching YouTube.
Okay. Hi, Julia. She'll hear me in 30 seconds.
But because of time, maybe you just type answer.
I can type.
As you wish.
Maybe if you think it might be of interest to everybody, can you tell me the question? I won't look. Otherwise, I'll get lost on my screen if I go looking.
Do you ever foresee spots for non-UM? I don't know what this means.
University of Michigan.
Maybe? So yeah, the program is nationwide. It's nationwide. Now, in our current form, so before we used to just select from everywhere, and often we didn't have a U of M student. Okay, you have to balance that because the administration at Michigan might say, why are we going through all of this bother and not sending any Michigan students? So we have some. Now in our current form, because half of the money comes from the university, from the endowment, those 3 students come from the University of Michigan. But the other 3 or 4, we have other support for, and then we look broad. We look all over the country, large schools, small schools, diverse schools. And we're in particular for those students looking for a diverse set of students. We're really looking for women and people who are Black, people of color, who aren't like me. Okay.
There is another question from Julie, so maybe you can go to Mattermost and answer, because we have to.
Okay, I will do that.
Yes, thank you, Steve. Thank you.
Okay, thank you. I'll stop my share.
Okay, so now we would like to welcome Andrei, who will tell us about another great tradition that started in 2010. That is organization of exhibitions called Science of the Large Hadron Collider. So yes, Andrei, I'll let you tell us about it.
Hi, everybody. Just to check, you can hear me, you can see the slides well, right?
Yes, yes, it's all okay.
Good. So, as was introduced, so this is about the exhibit of the Large Hadron Collider. And in a particular place, we have been doing this for the last 10 years. Let me first say a few words in general. So we all value fundamental science, but the target of this festival, Science and Engineering Festival, is just to bring awareness of the importance for general public, because it's not really for granted. And it was alarming even in very well-developed countries, like in this case, I'm talking about the United States, but in other countries which have strong history of science, it's not necessarily that youth is interested in science technology. So that was the idea which started in 2009, which started this festival. I will not talk much about festival, we can look it up, but as introduction to the festival, so it started in 2010. In 2009, the ideas were circulated, and the founder of this festival is an amazing person, Larry Bock. Unfortunately, he died in 2016 because he didn't see the last festival, which happened in 2018. But I communicated with him by email, by phone, at the time it was being planned, and I had no idea that he was a blind person at that time. So he founded 50 different startups, technology related, and he founded this festival. Again, in 2009, the first one on the National Mall. I'll show you some pictures. It's actually very interesting just to have all these exhibits, science exhibit, technology exhibits in front of the Capitol. And later it was moved indoors because he couldn't predict. At that time we were lucky, but what if there's rain or something? So all later festivals were moved indoors into this huge convention center where you can walk for probably half an hour just across the convention center, take several huge blocks from the Washington, D.C. And it's apparently the largest event housed in this convention center. So this is about the festival, but what I'm going to talk about is actually the exhibit which we put on the festival. So the name we gave it, the Science of the Large Hadron Collider. It was created by Hopkins CMS group. So it's not CMS specific, it just happens, we happen to be from CMS. So the first festival was in October 2010. You can see the link, you can find more details. Then I followed every 2 years. 10, 12, 14, 16, 18, and we were supposed to have it in April this year. And just because of the COVID-19, it didn't happen. There were a few other related exhibits related to HC, NYU, New York University, then later by FNAL, US LHC user organization. In addition to this, every 2 years, every year we have this exhibit at the local university physics fair. So there is a spring festival associated with this. There was a what we call physics fair, and I'll show you some pictures there as well. Back in 2010, we wrote this popular article. You can see more there. But basically, there's a picture from the very first one. You can see this is where we set up in the morning, and you can see Capitol here. Everything was put on grass here. You have these cubicles where you make exhibits. But we engage undergraduate students, graduate students, postdocs, faculty. In this case, everybody was from Johns Hopkins University. You can see people here. What exhibit? This is the exhibit was growing with time. This is the very first meanings of this exhibit. This we just set up in October 2010. So what we have there. So the important things there is to have something to show particles, and how can we show particles? There is a cosmic ray detector counter, and there is a cloud chamber where you can actually see traces. And the cloud chamber was the most popular one. Obviously, you need a dark room, so we had to create kind of dark rooms. You have dark clothes, you close it, and then people look, and it was amazing view for many people. We also substituted, supplemented with a few things like electron beam. So in EUA beam machine, this from our general physics lab, but you can actually see electronic beams, so you can show symmetric particles. In dark room, we had various literature hands out prizes. We actually had some quizzes people would answer, and we give prize. There was computer simulation. We started with a small laptop. Later, we went to a bigger screen. We set specific T-shirts to our LHC exhibits, and so we had posters, and this time the number of posters grew. But this is kind of the idea. On the next slide, you can see how this actually grew over time. This is one of the probably 2014 and 2016. This is how it went indoors, and it was huge. So it's only one small fraction of the whole convention center. So it takes several huge blocks in Washington, D.C. So they estimated it was about 350,000 visitors. Obviously, not every single visitor came to the LHC exhibit, but large fraction passed by, and a large enough number of people stopped by and interacted. So this is example here. We have the cloud chamber, dark room. People would go there. And we have people talking. Here we already engaged like people from Hopkins, the University of Maryland people standing here in the red T-shirt, and other people help here as well. But they come, visitors, and interact. Here actually live connection to CERN. I'll talk about this later. So on the screen we have two people who are actually at CERN in the control room, and people who are amazed to talk to somebody in Geneva. Just the fact they can talk to somebody in Geneva, the experiment happens, was really attractive to people passing by. We also have, as I mentioned, physics festival at Hopkins locally. We had it 16 times by now, and you can find more in the links here if you want to find more information. Going to the next slide. So in 2018, we actually joined forces, and there was an exhibit from now, Fermilab, and we explicitly asked the organizers to put us next to each other. So we had two cubicles on J2 side, two cubicles on the FNAL side, and we were next to each other, and everything was related to particle physics. Also University of Maryland, which is also local to DC area, and people from Fermilab who lived in the area joined the exhibit. So the one from FNAL was organized by the US LHC User Association, and the people leading this listed here in particular communicated a lot with Harvey Newman. So Harvey provided a couple of slides, which he asked to share, and so I include those two slides from Harvey here. So this is from the FNAL side of the exhibit. You can see their slides, so there are posters. There's a big poster we can take a picture next to, have the illusion you're actually on the ground there at LHC. There's a virtual reality, which I also talk about more later. And constantly there is a certain crowd of people waiting to see one part or the other and talk to somebody. So there's another picture from US Users Organization, LHC Users Organization. So this is the virtual reality. We can see, I'll also show a bit more later, which was a big hit there. The other thing we had is this virtual visit to CERN. It happens to be the Atlas control room. I'm from CMS, but there is not much of a difference, Atlas to CMS, so we just happen to connect to Atlas. So this is how it looked on festival in DC. There are practical considerations. So if you want to bring an exhibit to Washington, DC, there's still some travel away. So there is a limit to how much things you can carry. So here we took a big screen, but it was limited, but at Hopkins we could put a bigger screen. This example how we did at Hopkins. So there's a virtual reality put in the corner here where actually people in virtual reality and we project on the screen that people outside can see what the people with virtual reality can see. So it's more interactive. And you see cloud chamber here, computer simulation, this big screen connection to Geneva. And as I said, over time it was growing. So in the very first one, we didn't have virtual reality, we didn't have connection to Geneva. With the latest one, we had all those latest features. Just a bit more words about this virtual reality. In fact, this virtual reality was built by a student, a graduate student at Hopkins, Lucas, just because he's enthusiasm of computer games. So he built this box just on his own. It wasn't very expensive because he built himself. So the important thing is to have dedicated graphics card, modern CPU, and at least 8 gigabytes of RAM. So he used Windows 10, and this is the video connection you have, which you put for virtual reality, and the CPU and graphics cards is inside there. But then with a good enough power of your computer, you can see the visit. Again, we are from CMS, but we use the virtualizer Atlas. It doesn't really matter which one you show. For this festival in 12 this year, we actually prepared looking at, I believe Bell also had interest in virtual reality, but the festival didn't happen, so we didn't run it. But nonetheless, with a good enough computing, very interesting part of the exhibit could happen. The other, which was new for us since 2010, is the virtual visit to Geneva. And as it happened that former student working with me moved to Atlas, and that's why we connected to Atlas control room. So he kind of reached out to me and we connect to Atlas, but similar things exist in CMS. What's the most important in this case to have very enthusiastic guides, which makes a big difference. At the same time, it's labor intensive, of course. This is not something you can talk to hundreds of people at the same time. So you talk to a small group of people passing by. So this is probably the main challenge in this outreach is that it's a lot of effort for a crowd of several hundred people. You have to talk and engage with them for several hours. So this is very demanding, labor intensive, but other than that, this is very rewarding because this is one of those very attractive things as people in Washington, DC pass by, and it really stands out compared to all other hundreds of exhibits in Washington, DC when you can make live connection to Geneva. So this was very attractive thing there. So what else? The particle growth. So what I started from, the most important review, and this was started from the very first, this is in 2010, this is 2018. We used the 4-layer cosmic ray detector. This is part of our QuarkNet project. So we created it as part of the QuarkNet project, which for those who don't know, this is we created for high schools around the area. And we use one of those detectors for the exhibit as well. So those you have actually electronics you can count and you can do different experiments. You can remove those and put them in sequence and show that your counting will be changing depending if you do coincidence and so on. And there is a computer simulation actually shows how cosmic rays go through to illustrate how all of this happens. So this electronics, some people actually find very attractive. For some people, electronics is not as intuitive. So for those people, the very intuitive thing is the cloud chamber. And there you can see with your naked eye, looking at the particles going through the medium there. As it was very formal in 2010, by 2018 it became very formal. There are some legal requirements. For example, we had to bring radiative isotopes to Washington, DC in the convention center, so we had to fill the paperwork. Anything we did became much more formal. So the first time we brought stuff, essentially there was no paperwork to fill out. Now it's much more rigorous, more recent festivals. Nonetheless, all of this being filled out, all the substances, like you have to bring alcohol, you have to carefully account for this. But other than that, all of this is possible as long as you're careful. the final thing I want to say, we shouldn't forget about the kids. So while all those things which I mentioned are more like targeted to adults, high school level students, those who live in elementary school may not. So they may be interested to see some of the particles, but they don't really engage as much. And for those, we had various things like magnet things, like this linear accelerator. They really played a lot. So many kids play with this kind of model of linear accelerator created with the magnets. A lot of frozen stuff too, because in the LHC we have liquid nitrogen. So well, we bring the liquid nitrogen to model what we have. We have really cold temperatures, magnets, all those things. We have superconducting train in at Hopkins. Those bringing superconducting train to DC was sort of, we were limited. We didn't carry all this stuff. Weightless magnets. This ice cream, like with the liquid nitrogen, all of this attracts kids. So in the summary, let me say that public awareness of important science cannot take it for granted. So we developed this LHC exhibit with this in mind. So to make connection between what we do in science, technology, to the public. There are a number of relatively simple demonstrations which are possible to do, even to bring them long distance to another city to demonstrate it. We try to target all ages. It should be affordable to most university groups and most effective in connect. It's most effective in the context of a large event. So just exhibit by itself, you need to have a crowd of people where you show it. And what we found, this science festival or our local physics fair were very attractive places where to show it. So it happens either every year or every other year. And this way we are trying to engage the youth and keep us engaged as well. So this is also very rewarding in terms of we get connected, and all the students who participate in this also found it very rewarding. They get connected to everyday life this way as well. Okay, that's all, thank you.
Thank you, Andrei. Do we have any questions?
Nothing. Yes, Pedro.
Oh, thank you very much, Mira. Andrei, if I may be not polite, totally blunt and a bit stupid, can I ask you, was your stand visited by politicians? Being in Washington, D.C., I don't know, congressmen.
You're asking if politicians came to visit our exhibit. That's a question.
Yes.
So I haven't seen personally any politician coming in person to our exhibit, or if they did it, they tried to keep incognito, right? So they wouldn't tell who they are. So in that sense, no, I haven't seen somebody who would say, I'm a politician, I want to ask about science policy. That didn't happen. But it's possible they are there, but it's not really targeted towards politicians.
No, I understand it's targeted to young people and kids and all, but being in Washington, D.C., which is the hub of power in the US, that's one of the points where it will be great if politicians could at least take a bit of time to see such a big exhibit, because it was, I mean, what fraction of visitors you had? I mean, you had said there were 350,000 visitors.
So the whole festival estimates 350,000 visitors to the festival. If you wanted to ask me what would be the estimate of visits to this particular exhibit, it's certainly a fraction of it. It's maybe percent of this, or sub% of this. It's hard to say.
But it was lasting for how long?
It's a 2-day event. All of those were 2-day events.
Thank you.
It's a weekend. It's Saturday and Sunday. That's when people have time to walk around.
Okay, thank you very much.
Do we have more questions? I cannot see any hands up. I will go to Mattermost. No, I cannot see anything on Mattermost. Okay, so thank you, Andrei. It was very nice to see that other projects presented earlier were also helpful during your exhibition. And I hope this session is also inspiring for you for other ideas. Okay, last look if there is no more questions. No, so thank you very much, and we can move into the next talk by Carla, who will tell us about the Astroparticle physics outreach program for high school students organized by INFN in Italy. So Carla, are you ready?
Yes, I am ready. I just share my here. Share.
Yes, we can see your screen.
Yes, it's good.
Yes,
okay.
So you can start.
Yes. Good afternoon, everyone. And in my talk, I will tell you about this program, Astroparticle Physics Outreach for high school students, developed by INFN, and some public engagement activity carried out over the past 2 years in the framework of this OCRA. OCRA was born in 2018 as a national outreach project of INFN, with the aim of collecting within a national framework the public engagement activity in the field of cosmic ray physics, already present at the local level in 21 of the INFN division and laboratories. Practically all the major Italian cities are involved, as you can see in the map on the right of the slide. More information about this activity, about this program OCRA, you can find on the website as well as in the social page of the project. First of all, OCRA coordinates the International Cosmic Day for the INFN in Italy, helping to standardize the day's activity through the following phases, like seminars, measure with a muon telescope, video call and the discussion of the results, and finally also the questionnaire and the workout. In the last ICD, 1,000 high school students involved in 20 of the INFN division laboratory participated on the 6th of November 2019. Now, in this slide, you can find some statistics about this participation of the day. 14% of the approximately 1,000 participants were girls, most of them coming from scientific high schools, but also from classical high schools and technical institutes also, with an age between 16 and 18, class from 3rd to 5th. From 102 schools in 76 cities all over Italy. The event had good media coverage, as you can see, with both traditional and online newspapers articles, and also with radio and TV service. In this slide, you can also have some questionnaire given to the students. That it's possible to note that the majority preferred the seminars, unexpected for us, but following by the experimental measures and the analysis. The video call was less appreciated. The answer to the question shown in the graph on the top of the slide have all been very positive, except for that was your prior knowledge sufficient to follow the event? It's less of about 3.5 of both, especially for the younger one, we see. The other, after each edition of ICD, OCRA organized a scientific camp in various INFN laboratory. In fact, 2 students for each sites of ICD 18 were selected among the almost 800 participants in that edition of ICD via competition to join the OCRA Science Camp at Grassasso. The science camp took place in April of 2018, and were organized by the Gran Sasso Science Institute and by the laboratory of Gran Sasso of INFN. The activities involved seminars, a series of measurement field, the analysis of the data by the student under the guidance of the researcher, and a visit to the underground laboratories. The measurement aimed to determine the dependence of the cosmic ray flux on the altitude by means of a set of measurements carried out in several places around the Gran Sasso Massif. All data taking was carried out with the cosmic ray cube that you can see on the picture on the right. Telescopes composed of 4 double-plane horizontal scintillator level, orthogonal to each other. Each plane consists of 4 solid scintillator strips with a wavelength shifter fiber inside, carrying the light produced by interaction with muons to the end of the strip where it is collected by a silicon photomultiplier, which generated an electrical signal fired a blue LED, as you can see in the picture. For the OCRA Science Camp 2020, then this year, was scheduled at the National Laboratory of Frascati in April 2020, and involved the launch of an air balloon equipped with instruments to measure the flow of cosmic rays during the flight. Under the guidance of the researcher, 50 students would assist in the preparation, the launch, and analysis of the data. In this way, the students themselves would have been the protagonists of the experience, discovering what it means to do scientific research, work in the team, manage unexpected events, and solve various problems related to taking data in the field. But unfortunately, due to COVID-19, the camp was postponed to spring 2021. Until now, I have told about the activities common to all collaboration of OCRA collaboration. Now, I am going to introduce you to some of the local activity organized under this OCRA collaboration. For example, that reported in this slide, that we organized in Naples for 3 years, called La Scuola di Astroparticle. Sorry for Italian, but this is the name because it just related to the Italian students. That means at Astroparticle schools, which every year involved about 600 students from Campania region, not only on astroparticle items, but also in radioactivity, nano-optics, biosensor, accelerator theoretical physics, data acquisition technique, and so on. Through paths for transversal skills and orientation, PCTO in Italian, that is an innovative teaching method which through practical experience help to consolidate the knowledge acquired at school, test the aptitude of students on the field, enrich their training and guide their study path. All details can be found on the Facebook page of the project, and also this activity, unfortunately, due to pandemic, have been postponed to the next school year. But even if some of them went online, like reporting in this picture. In fact, after the visit to the muon telescopes that is in the Naples metro of the Tolled station, I invited you to visit if you just stay in Naples sometimes, and the activity in the Cherenkov telescope array laboratory in Naples, this activity went to the online, like you see on the picture on the button right. Then on the other activity on this aspect, even local, is reporting this picture like a PCTO in Lecce that allows the students to work together with the research to build a scintillator surface detector for the upgrade of Pierre Observatory. The activities carried out so far involve 10 students in Apulia, 10 schools, sorry, in Apulia, for a total of around 6,000 hours of internship. In the figure, some students are working in the Detector laboratory. Another activity is related to Pacini experiment in the Pisa. In fact, to repeat this experiment, some students from the Cecchioni Scientific High School of Livorno participated in a measurement led by research from Pisa in December. In the Naval Academy of Livorno, the student made the measurement and verified the decrease in event according to the depth using the Gamma Scout counters placed in the waterproof boxes. Measuring the radiation shield effect with Pacini's method is an exciting experience for students. In fact, unlike what happens in the laboratory, they are engaged in a series of multi-layer measurement with the difficulty of solving problems and also identify the reason for an anomalous behavior of the data due to systematic reason, for example. The data are described by an exponential two-parameter function that allows refined statistical analysis and therefore an introduction to basic concept of statistical data treatment, such as fit with the least square method that can be done by hand by the student. Also another activity in Rome, in collaboration with the Cariati Scientific High School and with the AB project, a company specialized in light balloon flight, realized a stratospheric balloon launch in order to measure the flux of cosmic rays as a function of the altitude, like that proposed for the camp, scientific camp of this year. The launch of MOCRIS, this is the name, measurement of cosmic ray in stratosphere of the project, started in Campitello Silano, in a region, a little place in Calabria region, and reached an altitude of 13.4 kilometers in the atmosphere. The collected data allow us to study the physics of the atmosphere also, and the dependence of the flow of cosmic ray on the quota. Then the last one, to finish this roundup of the local activity, the last one I show you the developed by the Milan group that consists in a summer workshop of high school students. These workshops are full-time over 2 or 3 weeks, and during these, around 10 students from Milan area are provided with the possibility to do some hands-on astroparticle physics always. They analyze data from the Pierre Observatory, not only, but also the Boraxino experiment, follow classes and cosmic rays, neutrino and dark matter, and build detectors such as cloud chambers and scintillators. And to finish, during the pandemic, however, many OCRA activities were postponed or even cancelled, unfortunately. But others were carried out, such as the online activity reported in this slide, that I will show in the last few slides. In this, you see the path of cosmic rays developed for high school students, especially those who took the last year's exam. All these activities are in the OCRA website, and I just indicated on the left of the slide, and is divided into various interactive laboratories, like that reported in this slide. In fact, you can see this educational experiment made with simple devices to measure cosmic muon and describe their behavior. In fact, each experiment is dedicated to the description of a measurement. With the available data, it is possible to be guided in the analysis that leads to the muon rate measurement track reconstruction with the cosmic ray cube telescopes I showed before you. measurement of angular distribution muons like Toledo muon telescopes, measurement of muon, like for example, also possibility to have a muonography under the metro of station in Naples, measurement of muon intensity as a function of zenith angle like done in the ICD, measurement of muon as a function of height in the atmosphere like that in balloon flight, and measurement of muon as a function of depth in water like Pacini experiment. All these activities have been developed to be interactive using Excel, but also Python with Google Colab. And all the activity have been developed to be to be analysis of data from muon telescopes, but also from experiments like the Pierre Auger Observatory, like you can see in this slide, where you can see the spectrum of Auger data and the asymmetry. Then my conclusion. OCRA has been active for only 2 years, but has grown and involving almost all INFN division. OCRA organized not only ECD and CAMP as its common activity, but also a lot of many local activities. And during the pandemic lockdown, new online activity to bring students to cosmic ray through muon detection and analysis of experimental data. And the synergy between the groups and also between research and high school teachers are very fruitful and fundamental for developing a new educational activity. Like that, it's on that now we are working. Like for example, the Pierre Auger Observatory Masterclass that we plan to organize the next years. And thank you for your attention. If you want more information, please contact us. Thank you.
Thank you, Carla. Congratulations for a program that is only 2 years old. So, do we have any questions from the public? Pedro, this time I noticed you.
Carla, thank you very much for this very impressive effort that you're doing in Italy, and also for other collaborations which will profit. What's the amount of number of students in the camp, and how do you select them? They are school students, right?
Yes, yeah, they are high school students, right? Yes. And we involved about 50.
50 per edition.
Per edition, yes. And we selected during the ICD International Cosmic Day that in different way. One of these is just a count at the end of the day, just a questionnaire to understand if these involved the students in the ICD just understand what they perform on this measurement, on cosmic muon measurement, and also in another way, like reports on the measurement, like an article, scientific article that just explain the detectors and the analysis of the measurement. Then we have these two different modality mode to select these 50.
Okay, just to understand also related to the International Cosmic Day, in slide number 4, you report on 65% of 5th, 4th, and 3rd. These would be the years at the secondary school?
Yes, the years, yes. The last one, the medium, and the third. Then this means 16, 18 years old students. This is the target of this year's high school, yes.
Okay, thank you very much.
Thank you to you for these questions. Thanks a lot.
Do we have more questions to Carla?
Martina, I have a question.
Okay, go ahead, Despina.
Hello, very interesting to find out about all these activities. I just wanted to ask, is this done for the students in the frame of alternanza scuola-lavoro?
Yes, now the alternanza scuola-lavoro in Italy names PCTO, path to it's another name, but it's quite the same. That's changed. In Italy, the name is before this year, like alternanza scuola-lavoro. Some of our activities done inside this framework, but not only in this framework. Just, for example, a scuola di Astroparticle in Naples is done in this framework with 600 students involved on the alternanza scuola-lavoro, PCTO now. Yes.
Okay, thanks.
Thanks.
Is there anyone else who would like to ask a question? In the meantime, I can ask a question. I can profit.
Oh, thanks.
So I see that you have quite an impressive number of press coverage. Are you doing anything towards like reaching out to the press, or is this like organically coming your way? So the press is interested naturally by hearing about it.
Yes, this is a very important question because when in the past did the International Cosmic Day just in a few cities at not organized together, but just okay in Naples or in Rome and so on, without to collect no interest on the press, on the radio, TV. When we just organize all together with the help of INFN communication office and to, how to say, share the information all around Italy with 1,000 students involved, that is the key that the press was very interesting to this activity because involved a lot of city, a lot of students all together organized, and this I think that is a successful things to do, and this we just have this how to say
definitely it's a great success, but it means that you are preparing a press statement, press release with INFN. Okay.
We prepare a press the day before the ECD, send to our contact and all around the Italy in the press and the online paper and so on. And at the end, we succeed to have this, how to say, useful, good response from the press. Yeah.
Okay, thank you very much.
Thank you to you.
Okay, so I cannot see any up, so we can thank you, Carla, for a very nice and interesting talk. And we can move to the last one for today. And Nicolas Arnaud will tell us about engaging diverse audiences worldwide to the quest for gravitational waves. So it's about the communication aspect of gravitational waves discovery.
Yes.
So go ahead, Nicolas.
You should see my slides.
Yes, we do. Mm-hmm.
Okay, so I'm going to report on behalf of the Virgo collaboration and the LIGO scientific collaborations that are working together to discover and study gravitational waves. So after a brief summary of what we are trying to detect and how we do that, I will focus on outreach and communication. So first about the scientific results with the public alerts that we try to send to the astronomical community and to the general public each time we have a trigger that would be significant enough. I will talk about the scientific announcements and show what we do to promote LIGO Virgo members. Then I will switch to the second part that will be reaching out diverse audiences, social media visits, science festival, art and science, and other things that we do, for instance, for visually impaired people. And finally, I will briefly mention this iGrav initiative and then conclude. So LIGO and Virgo are two collaborations that are operating 3 detectors, 2 in the US, Hanford in Washington State on the left, and Livingston on the right, which is in Louisiana State, and Virgo that is in Italy. So these detectors are looking for gravitational waves, and they are individually responsible for taking data, but as soon as the data are there, all the analysis is done jointly by the 2 collaborations, because you're looking for extremely tiny signals buried into noise, and so a single detector is usually not enough to claim a detection with certainty. So that's why we work together. And soon we should be 4, because the Kagra detector in Japan is basically ready and will be part of the next joint data taking. So those detectors, as you can see on the pictures, are giant Michelson interferometers with various subtleties and special design in order to get the suitable sensitivity and to be able to see signals in the noise. So we are alternating observing run and shutdown periods to do upgrades and commissioning. And the most recent data taking period is called O3. It started April a year ago and ended up at the end of March this year, about a month earlier than anticipated because of the pandemic. And what is good during this run is that we published 56 non-retracted public alerts. That is potentially 56 potentially interesting gravitational wave triggers that the astronomical community can try to follow up. And we have already some some papers about the first detections, but more to come. So those public alerts, our goal is not only to detect gravitational waves, but also to help to locate the source in the sky. So in low latency, that is within a few tens of minutes at most, following the online analysis of the data, we send those alerts that include a sky map, like the one you can see at the bottom left of the slide. So as I said, 56 during O3, and you can see how that number increased with time. So this goes through a multi-stage process, obviously first internal to LIGO and Virgo, and then once the trigger has been validated, has been vetted by humans, we send it to the astronomer community through the GCN network. But we also send it to the general public through either automated tweets, like the one you see here, or to this very cool Chirp app that you can get more information. It's developed by colleagues from Birmingham, where you can receive on your phone LIGO Virgo alerts. And then humans take over, and usually you get blog posts after a few hours. So one of the things that we try to do well is when we have scientific announcements, new discoveries, new results. We have the official part that is done fully joint and fully coordinated between LIGO and Virgo. So you can imagine that that makes the whole process a bit more complex. You have to deal with different time zones, different teams, different target audiences, different ways to convey the messages, and so on. So that's not so simple, but so far that has been quite successful internally, and we triggered some excellent media engagement. So on the left, you have one detection announced on the LIGO side, and on the right, another of these early or free detections announced on the Virgo side. So one thing that is good is that parallel to the scientific publication, we release various companion products in addition to the press release and the website announcement I just showed you. There are, of course, social media posts, also media resources, various animations, graphics, pictures. So on the left side, you have an example from a French artist called Alex Hendricks. And if you want to see the whole video, you can click on the link. And on the right, this is an animated video showing basically how people could use some open tools to investigate more the sky maps that we have for the different levels. Okay, we are also targeting students and teachers. So we do what we call science summaries for each important article, and we do that multilingual because, as you know, if we can reach out to people in their language, that helps a lot. And we use really the diversity of the collaborations to get as many languages as possible, including some Native American languages. And so you have an example of the first page of one of these science summary on the left side. And we try to accompany that with a fact sheet, basically a summary of the key numbers for a given results. And we also try to make some basic infographics, as you can see in the video. So there are additional things that we try to populate discovery after discovery, announcement after announcement. And one of them is this plot that is called masses in the stellar graveyard, where you can basically see for each time you have a compact binary system merging, you have information about the two initial objects that collide and produce another object. So in blue and purple, these are the black holes, and in yellow and orange, you have more of the neutrons. We also produce animations like the one at the bottom of the slide, that is basically showing how the Virgo sensitivity has improved over the time. So you see this red complicated curve that is slowly going down over time, and the lower the sensitivity curve, the better the sensitivity, because that's a measurement of the noise level. So it's a very complex curve with a lot of features, a lot of noise superimposed. So one way to summarize it with one number is what is shown as the bottom. We have this range, which is basically a distance up to which you can detect a given source. And so as the sensitivity curve goes down, this distance goes up. And that's basically what the red dot is showing you as well. Also, we try to focus on our people, LIGO Virgo. And a great example, I think, has been done on the LIGO side with this website, Humans of LIGO, where you can really see a lot of things about individual people who all have interesting stories to tell. On the social media, we are active on Twitter, Facebook, Instagram, and YouTube with various level of followers and various posts, but we have a few dedicated people that post a lot of things, and there are a lot of reposts and stuff. Another big aspect also are the site visits that have been read until a few months ago. So there are a lot on all three sites. General audience really, including students and teachers. Basically, things started to grow quite significantly when we had the first detection announcements in 2016 and the year after. And basically, the curve has been steady increasing since that, as you can see on the chart that is on the right part of the slide. So you see that this is the example for Virgo. You have basically 7 times more visitors, 5 years in 5 years. So that's about, if you count by week, excluding the holidays, it's more than it's about 200 people per week steadily. So that's a lot, and that's actually beyond the capability of reception that we have at Ego, which is the site of Virgo, because everything has been done so far on the voluntary basis. So we tried to accept all the visit requests. Now, of course, things have changed, but that was really a big job. At LIGO and Ford, so in Washington State, they plan to construct a science center. There is already one in the other LIGO site, and it should be ready in about 1.5 years from now. So that was before the pandemic. Other things are events that we organize on site. Again, that was before the COVID. We'll see what we can do later. So we have this European Researchers Night that we do every year. And with collaborations with astronomical amateurs, we are also organizing observation evenings. When the night comes, people look at the telescope, and before they visit the site and hear about gravitational wave searches. So now, of course, we have moved to more virtual visits. That has always been pre-existing in our mind, but now there is an emphasis on that, and we try to develop that quickly. That will be tried during a science festival in Genova in October. Now we are also in a period of upgrades. So we have purchased various cameras to produce time-lapse videos showing the work. And we encourage local LIGO Virgo groups to make online conferences for the local audience. And so that's an example from the Netherlands. So if you understand Dutch, you can look at the record. This is a set of pictures taken at various conferences or public events where LIGO was. And so they usually come up with some booths that are always very well attended. On the Virgo side, we try to participate to exhibitions where we show actual pieces of Virgo or things that are built to show how Virgo works. So at the top, you have a mirror of the first generation of the Virgo detector that is on display with the final stage of its suspension. On the middle part, you have some pictures taken in Paris at the famous science museum Palais de la Découverte, where we were trying to show little table interferometers and also some pendulum to show how they can be used to attenuate the seismic vibrations. And we are planning to participate to this EASOF exhibition at Trieste after summer. That should be a big, one of the first big post-COVID events. We are also in LIGO Virgo part of this Origin network that you probably all know about, and it's very nice to see that we can show what we do in this exhibition and that are mixing art and science in a very nice and constructive way. We have also collaborations with artists. This is on the Virgo side. We had contact with the Thomas Saraceno, that you may know as Spider-Man, the guy that is doing a lot of exhibits with spiders, spider nets, and stuff like that that are very nice. And he did one in Palais Tokyo in Paris 1.5 years ago now. And among the exhibition, there was a multi-messenger room that was gathering data, sometimes live, from various experiments, including Virgo, and turning them into images and sound that the audience could grasp more easily. As I said at the beginning, we are also trying to reach out more audiences. So the first picture here was taken during a science dating on the rowing boat in Lyon, France. So you are really on this boat with rows, just a couple of people and the scientists. So you have no way to escape, and you have to listen to the presentation until the end. As I said, we are also working for visually impaired people with a 3D detector model and some sculpture showing what a signal would look like. We are in touch with blind artists. And there are some sonification projects going on, like trying to turn a gravitational wave sky map into sounds so that people could have an idea of where the source is located in the sky. And we have another project completely different that was postponed to next year due to the COVID, which is called Virgo in Jail, which is a project to make some simultaneous conferences in prisons in various countries at the same time. So one word before concluding about iGrav. So building on the very good example from IPOG, we are trying to build a gravitational wave, or I should rather say gravity-oriented outreach network, gathering all the experiments and the projects together, and people experts in outreach, communication, and science educator. That started about a bit more than 2 years ago when we had this very nice joint IPOG LIGO Virgo session at Virgo. So here you have a group picture with the Virgo main building behind you. So we came up with the acronym iGrav, International Gravitational Wave Outreach Group. And progress are there, but quite slow. The emphasis so far has been on various working groups that are trying to work together. We had the first meeting yesterday, last year, after the Amaldi conference, that is a bit the equivalent of ICHEP, if you want, for gravitational waves, on a slightly smaller scale, of course. And we had another global meeting earlier this week on Monday and Tuesday, and there were 50, 60 people attending, which is not too bad. So we will keep pushing on that, hoping that we can meet again in person very soon. So this period is busy and exciting for LIGO, Virgo, and soon CAGRA, with more and more signals detected as the detectors improve. And keep in mind that the first detection is only 5 years old, kind of. And so that's also a busy and exciting period for the outreach groups of these collaborations. We have to cope with the detections and the announcements and convey our excitement to the general public. So we are trying to use as many channels as possible, from the most classical or obvious to the most modern or technological. We really try to care about all audiences. And one thing where we put the emphasis is on the multilingual aspect, because that's really the way to reach out to people. We are also trying to develop specific tools depending on the audience that we are targeting. And that's all these projects in parallel that I showed you before. And LIGO Virgo is successful because we managed to work together, two collaborations that were independent at the origin. So that's a big challenge, and I think we are pretty successful. And that's why we are now trying to go the step further, building this iGrav network cross experience. So we should restart taking data sometimes in 2022. We still have to understand how the schedule will be changed and impacted by the pandemic, but we hope to start sometimes in 2022. And in the meantime, we will still work on the free data. There are a lot more results to come. Thank you, Maria.
Thank you, Nicolas. Do we have questions from the public? I have a question. So it's what you presented is really impressive. Do you have a team that is working on outreach and communication, or you are doing it on your own? I hope not. Or other researchers are helping you?
Of course, I am just a speaker today. We have quite a few people involved, both on the Virgo and on the LIGO side, but there is a lot to do. So I'm not sure we are enough. But yes, there are dedicated people on both sides working on that. So clearly,
okay. Yes, because
that's a collective effort.
Yes, because the amount of work you presented is really impressive. And also the plans you have, this looks impressive as well. Okay, any questions? I will have a look at the Mattermost. No, we don't have anything here. Okay.
Even Pedro is tired, so I was expecting a question from him, but maybe even him is tired.
No, it's just that we presented iGrav last year, but of course we are eagerly looking forward to work together.
Okay, so thank you, Nicolas, for your talk. And that was the last one for today. So from what I understand, we are free to stay and discuss if we like. Mira, is that correct?
Yes, yes. If the mood is ready.
Yes, if there is a mood for discussion, we can stay in this room. And if not, we better go to sleep because we meet at 8 a.m. tomorrow, yes?
Yes.
7 for some people.
For some people, exactly. So we saw a great spectrum of different projects, from gaming to educational